Take a slow breath in and let it out. Find a comfortable position, wherever you are. Let your body settle, let your muscles soften. You don't need to hold on to anything tonight. You can simply let go. Tonight, we are going on a journey. Not a hurried one, not a dramatic one. A slow, quiet journey, out past the edges of everything familiar, into the deep, dark heart of the universe itself. We are going to spend some time with one of nature's most mysterious creations. Something ancient. Something almost impossible to imagine. Something that bends the very fabric of reality. We are going to learn about black holes. But there is no rush. Each idea will come to you gently, like a wave arriving softly on a shore. You don't need to hold on to every word. Just let them wash over you. Some will settle in quietly while you sleep, and that is more than enough. So let yourself breathe. Let your eyes grow heavy, and when you are ready, let the universe begin. There is a word we use so casually now. A word that conjures images of swirling darkness, of light being swallowed whole, of the very edge of the knowable universe. That word is black hole. And yet, as familiar as it sounds to us today, it is surprisingly new. For most of human history, these objects had no name at all. And for much of the 20th century, even after scientists began to suspect they might exist, they were given names that were far less evocative. Gravitationally collapsed stars. Frozen stars. Names that were accurate, perhaps, but that carried none of the weight, none of the poetry, of what these things truly are. It wasn't until 1967 that the name we know today was given to them. A physicist named John Archibald Wheeler, a brilliant and deeply thoughtful man, used the phrase black hole during a lecture. And something clicked. The name spread. It captured something that no equation ever quite could, the sheer, absolute darkness of these objects. The sense that here was a place from which nothing returns. Just two words. And yet they changed the way humanity pictured the cosmos. So the next time you hear the words black hole, know that they are younger than many people alive today. The universe had been making them for billions of years before we ever found the right words to describe them. And now, here is something that might surprise you, something worth carrying with you gently into sleep. The man whose mathematics made black holes possible, one of the most brilliant minds in all of human history, refused to believe in them. Albert Einstein. The very same Einstein whose equations, published in 1916, quietly contained within them the mathematical prediction of black holes, that man spent years trying to argue that they could not possibly be real. He felt certain that no physical process in nature could compress matter so severely, so completely, that it would collapse into something so extreme. He tried, mathematically, to find the error, to show that nature would find a way to stop the collapse before it reached that point. He wrote papers. He calculated, he reasoned, and yet the universe, as it so often does, paid him no attention. Black holes are real. We have seen them. We have photographed them. We have detected the ripples they send through space when they collide. Einstein's own equations were right, even when he wished they weren't. There is something quietly wonderful about that. Even the greatest human minds are sometimes wrong about the discoveries hiding inside their own work. The universe is always a little larger, a little stranger, a little more extraordinary than we dare imagine. Let your breathing slow a little more now. There is nowhere to be, nothing to do, just this soft darkness around you, and the quiet voice of the cosmos. At the very center of a black hole, there is something that physicists call a singularity. It is a point, or perhaps something so small that the word point barely applies, where all of the mass that created the black hole has been compressed into an infinitely small space. Infinite density. Zero volume. a place where the numbers in our equations stop making sense. And that is not a poetic way of speaking. It is a precise and somewhat humbling one. When physicists try to apply our best understanding of physics, including Einstein's own theory of general relativity, which describes gravity with extraordinary accuracy everywhere else in the universe, to the singularity, the equations produce what mathematicians call nonsense answers. Infinities where there should be finite numbers. Breakdowns where there should be solutions. The singularity is, in the most literal sense, the edge of human understanding. It is the place where our maps run out, where the territory continues, but our tools to describe it do not. Scientists believe that somewhere beyond what we currently know, in some deeper, as yet undiscovered theory that unites gravity with quantum mechanics, there may be an answer. A way to make sense of what lives at the center of a black hole. But for now, it remains one of the most profound open questions in all of science. And there is something strangely peaceful about that. The universe still holds secrets. It always will. You might be wondering, what actually makes a black hole so extreme? What separates it from, say, a very dense planet or a very heavy star? The answer is compression. Not just mass, but how small that mass is packed into. Consider the Earth. Our planet is large, by human standards. It is nearly 13,000 kilometers across. It contains an enormous amount of matter. And yet, standing on its surface, you can jump. Gravity holds you here, but it doesn't crush you. Light travels freely away from it in all directions. Our planet, for all its size, is not particularly extreme. But now imagine taking every atom of that same Earth, every mountain, every ocean, every iron core, and compressing it. Squeezing it tighter and tighter and tighter. Not stopping until the entire planet is the size of a marble. Something small enough to hold in your hand. At that point, at that almost inconceivable density, Earth would become a black hole. The gravity at its surface would be so powerful that nothing could escape. Not air, not matter, not even light itself. The same planet, the same mass, but packed so tightly that the universe around it would be forever changed. That is the key to understanding black holes. They are not simply heavy things. They are things that have been made impossibly, unimaginably small. And in that compression, something fundamental about the nature of space and time is transformed. Let your body feel heavy now. Comfortably heavy. Let the weight of you settle into wherever you rest. There is no need to carry anything tonight. Far out in the cosmos, 9 billion light-years away, so distant that the light we observe from that place left before our solar system existed, two black holes are dancing. They are both supermassive. Each one contains the mass of millions or billions of suns, packed into a region of space smaller than our solar system. And for billions of years, they have been circling one another. A slow, vast, gravitational waltz. Each orbit taking approximately 2 years to complete. Astronomers at Caltech discovered this cosmic dance by doing something extraordinary. They went back through 45 years of old radio telescope observations and pieced the pattern together. Decades of data, collected by scientists who didn't even know what they were looking for, quietly containing the signature of two giants locked in an embrace across the universe. That dance will not last forever. Slowly, over timescales almost too long to imagine, the two black holes are drawing closer. One day, perhaps millions of years from now, they will merge. And when they do, the energy released will send ripples through the fabric of space-time itself, traveling outward in every direction at the speed of light. But for now, they dance. Quietly, patiently, 9 billion light-years away. Stay with me gently. Let each breath carry you a little deeper into stillness. When we think of black holes, we tend to imagine things of immense, almost incomprehensible size. And many of them are. But here is a quieter, stranger thought to rest with. Some black holes may be small enough to fit inside your pocket. In the very first moments after the Big Bang, in the dense, chaotic, unimaginably hot early universe, conditions may have been extreme enough for tiny concentrations of matter to collapse directly into black holes. These are called primordial black holes. And unlike the black holes that form from dying stars, they were not born from any explosion. They were simply squeezed into existence by the pressure and energy of the early cosmos itself. Some of these primordial black holes could have been extraordinarily small as a single atom, or even smaller. And yet they would still carry mass, still bend space around them, still be, in every technical sense, black holes. The smallest of these have likely evaporated over the billions of years since the Big Bang, slowly releasing their energy in a process we will return to later in our journey tonight. But some, the larger ones, may still be out there, drifting through the universe, completely invisible, completely undetected, patient and dark and ancient. The universe is under no obligation to make its strangest objects large enough for us to see easily. Sometimes the most extraordinary things come in the smallest possible packages. And speaking of the early universe, here is a thought that sits right at the very edge of current science. Something that has not yet been proven, but that some cosmologists take very seriously indeed. We know that most of the matter in the universe is invisible to us. We cannot see it. We cannot detect it directly with any instrument we have. And yet we know it is there, because of the gravitational influence it has on the galaxies and structures we can observe. We call it dark matter. And some scientists have begun to wonder, could there be black holes made not from ordinary matter, but from dark matter itself? Black holes that formed in the earliest moments of the universe, when dense concentrations of this invisible substance collapsed under their own gravity, long before the first stars ever ignited? These hypothetical objects, sometimes called dark matter black holes, would be unlike anything else we have catalogued. They would represent the first direct link between two of the deepest mysteries in modern physics. Dark matter, which we cannot see, and black holes, which we can barely observe even when they are made of ordinary matter. If they exist, they are out there in the darkness, formed before stars, before galaxies, before almost anything we would recognize as the universe. Science at its edges is a place of beautiful uncertainty, and sometimes the most extraordinary discoveries are the ones hiding in the spaces between what we already know. Let your thoughts grow softer now. Let them drift like dust through deep space. You are doing beautifully. For all their mystery, most of the black holes in the universe are born from something we understand, or at least something we can picture. Stars. Enormous, magnificent, burning stars. When a star much larger than our Sun, one that contains more than about 20 times the mass of the Sun, comes to the end of its life, something extraordinary happens. For millions or billions of years, that star has been held up by the energy of nuclear fusion at its core. Hydrogen being fused into helium. Helium being fused into heavier elements. A constant, roaring outward pressure pushing back against gravity. But eventually, the fuel runs out. And when it does, the balance breaks. Gravity wins. The outer layers of the star come crashing inward with unimaginable force, then rebound in a catastrophic explosion called a supernova, one of the brightest and most energetic events in the cosmos. And at the center, where the core was, what remains is compressed beyond any material strength to resist. Atoms are crushed together. The very structure of matter gives way, and a black hole is born. It is, in a strange and beautiful way, the universe recycling itself. A star that spent its whole life as a source of light, becoming in its death a place from which no light can ever escape. The universe's most extraordinary transformation. And there is more than one way for a black hole to be born. Not all of them come from a single dying star. Some come from a collision, a merger. Two incredibly dense objects finding each other across the void and becoming something new. Neutron stars are the remnants of stellar explosions, objects so dense that a single teaspoon of their material would weigh billions of tons. They are extreme by any measure. And yet they are not black holes. They are held in a kind of impossible stability by the quantum mechanical pressure of the particles packed inside them. But when two neutron stars find each other, when their orbits slowly decay and they spiral inward and finally collide, that stability can be overcome. The combined mass may be enough to push them past the threshold, and in the moment of their merger, a new black hole is born. This event is not quiet. The collision produces gravitational waves, ripples in the fabric of space-time, traveling outward at the speed of light. And it also produces gamma-ray bursts, intense beams of radiation that for a moment can outshine entire galaxies. Two of the most energetic phenomena in the known universe, happening simultaneously in a single violent instant. Black holes, it turns out, can be created in more than one way. The universe is endlessly inventive in finding paths to its most extreme creations. And finally, as we near the end of this first act of our journey tonight, one more thought to carry with you into sleep. Between the stellar black holes born from single stars, which might contain a few to a few dozen times the mass of the Sun, and the supermassive black holes that sit at the centers of galaxies, which can contain millions or billions of solar masses, there is a middle ground. A category that, for a long time, scientists weren't sure actually existed. Intermediate mass black holes. Objects containing hundreds, or tens of thousands, or even hundreds of thousands of times the mass of the Sun. Not the stellar remnants of a single star. Not the ancient giants at galactic centers. Something in between. For decades, these objects were theorized but never clearly confirmed. The universe seemed to offer examples at the extremes, but the middle ground remained elusive. Were they forming in dense clusters of stars, where multiple black holes might merge together, growing larger with each collision? Were they left behind by the first generation of enormous stars in the early universe? Slowly, carefully, using some of the most sensitive instruments ever built, astronomers have now found them, confirmed them, added them to our catalogue of the universe's extremes. The family of black holes is larger and more varied than we once imagined, and we are only beginning to understand all of its members. You have traveled far tonight. 9 billion light-years to watch two black holes dance. Back to the first moments of the universe to find primordial ones no bigger than an atom. Into the heart of dying stars to watch new ones be born. And you have done it all without leaving the quiet warmth of where you rest. Let your breathing deepen now. Let your mind grow still. The universe is vast beyond all imagining, and it will be here tomorrow, and the night after, and every night that follows. There is no need to hold on to any of it. Just let the darkness be gentle. Let it be the comfortable, familiar darkness of a clear night sky. If you are just arriving, that is perfectly all right. And if you have been here since the beginning, drifting gently through the story of how black holes are born, welcome to the next chapter. Take a moment now to settle, to adjust, to let whatever thoughts have been quietly running in the background of your mind begin to slow and soften. There is nothing that needs your attention tonight except this: the quiet dark, the slow breath, and the universe spreading itself out before you in all its patient, extraordinary strangeness. In our first act, we watched black holes being born, from dying stars, from colliding neutron stars, from the pressured chaos of the very early universe. We gave them their name, and we met the man who refused to believe they were real, even as his own equations quietly insisted otherwise. Now we go deeper. Now we step closer to the beast itself. Not to be afraid of it, there is nothing to fear in understanding, but to really look at it. To ask, what is a black hole, truly? What happens at its edges? What does it do to the space and time around it? What would it do to you if you fell in? Let your breathing slow. Let the weight of your body sink downward. You are safe and still and warm. And we begin. Imagine you are standing on the surface of a planet, any planet, and you throw a ball straight up into the air. The ball rises, slows, and falls back down. Gravity has won. Now imagine throwing it harder, much harder, hard enough that the ball travels a kilometer up before falling, then 10 kilometers, then 100. The harder you throw, the higher it goes before gravity pulls it back. There is a speed, a specific, calculable speed, at which if you threw something hard enough, it would never come back. It would escape the planet's gravity entirely and drift away into space forever. We call this the escape velocity. For Earth, it is about 11 kilometers per second. For the Sun, it is much higher. Now imagine an object whose escape velocity is higher than the speed of light. That is a black hole. At a black hole's boundary, a threshold we call the event horizon, the escape velocity reaches exactly the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses that boundary can ever leave. Not matter, not energy, not information, not light itself. The event horizon is not a wall. It has no surface. You could cross it without feeling anything unusual in the moment of crossing. But once you are on the other side, the geometry of space and time has changed so completely around you that every possible path forward, in every direction you could ever choose to move, leads inward. Toward the center. There is no outward anymore. It is perhaps the most absolute boundary in all of nature. And it exists not because of any physical barrier, but simply because of the shape of space-time itself. Just outside that boundary, just beyond the event horizon, in the region of space where light has not yet been swallowed, something strange and beautiful happens. Gravity is still extraordinarily powerful here. Not quite powerful enough to prevent light from existing, but powerful enough to do something remarkable, to bend the path of light into a curve. And at just the right distance from the black hole, that curve becomes a perfect circle. This region is called the photon sphere. In the photon sphere, light travels in orbits. A beam of light, moving at the fastest speed anything in the universe can travel, finds itself curving so severely around the black hole that it loops back on itself. It goes around and around and around indefinitely unless something disturbs it. In theory, if you were positioned at the photon sphere and looked directly ahead of you, you would see the back of your own head. Light from behind you would curve around the black hole and arrive at your eyes from in front of you. It is the kind of thought that the mind doesn't quite know what to do with. Light, bending into circles. Space, curved so deeply that the very idea of a straight line loses its meaning. Let that image rest in your mind gently. Light, looping forever, just beyond the edge of the dark. Now, our black hole is spinning. And most black holes do spin, as we will come to shortly. And a spinning black hole does something to the space around it that has no real equivalent in ordinary life. It drags it. Imagine stirring a spoon through honey. The honey near the spoon gets pulled along with it. The rotation of the spoon drags the honey in the same direction. Now replace the honey with the fabric of space-time itself. Replace the spoon with a black hole rotating millions of times faster than anything we experience on Earth. The result is a region around the spinning black hole called the ergosphere. Inside the ergosphere, which exists outside the event horizon, in space that is technically still escapable, you cannot stand still relative to the distant universe. It is not that the gravity is too strong to escape. It is that space itself is moving, being dragged, rotating with the black hole, and you are carried along with it whether you want to be or not. Even light, inside the ergosphere, is dragged in the direction of the black hole's spin. The ergosphere is not the point of no return. You could, in principle, enter it and leave. But while you are inside, the rotation of the universe around you is not optional. You move with the black hole, because space itself is moving with the black hole. It is one of the strangest properties in all of physics. Not just matter warped by gravity, but space and time themselves, set into motion. Let your body feel utterly still now. And while you rest in that stillness, consider this: the universe itself is almost never still. Every known black hole rotates. Every single one. This makes sense. When we think about it, the stars that collapse to form them are themselves spinning, and as the core collapses and shrinks, that spin accelerates, the way a spinning ice skater pulls in their arms and turns faster. The rotation is inherited, and then amplified enormously. Some black holes spin slowly, by cosmic standards. Others spin with almost unimaginable speed. The record holder, a black hole called GRS 1915 plus 105, completes more than 1,000 full rotations every second. 1,000 times per second, this object containing several times the mass of our Sun is spinning on its axis. At its equator, the fabric of space-time is being dragged around with it at a substantial fraction of the speed of light. The effect this has on the space around it is called frame dragging. Space and time near this black hole are not simply curved, as they would be around any massive object. They are twisted, wound, pulled into a kind of helix by the relentless rotation. We can measure this. We have instruments sensitive enough to detect the effects of frame dragging in our own solar system, around our own relatively sedate and slowly rotating Sunday. Around a black hole completing 1,000 rotations per second, the effect is extreme beyond easy description. The universe is not a still place. Even its darkest objects are in furious, constant motion. And that spinning leaves a mark. A lasting one. Carved not into any physical surface, but into the fabric of space-time itself. In 2005, astronomers studying the X-ray light flickering near a black hole noticed something unexpected. The patterns in that light, the specific rhythms and signatures of the radiation coming from the hot material swirling near the event horizon, were identical to patterns that had been observed 9 years earlier. Not similar. Identical. The interpretation was striking. The spinning black hole had carved a kind of groove into space-time around it. A persistent structural imprint. Like a record pressed into the fabric of reality itself, spinning around and playing the same patterns of light over and over for nearly a decade. Space is not an empty, passive stage on which events happen. Near a black hole, it is something that can be shaped, worked, impressed upon. It carries marks. We tend to think of the universe as immaterial, as though space is simply the absence of things. But around a black hole, we are reminded that space is something. It bends. It drags. It holds the imprint of the forces acting on it. And in the right light, literally, we can read what has been written there. Near a black hole. Something that is very difficult to fully grasp, and yet something that has been confirmed, measured, and found to be precisely as strange as it sounds. Time. Einstein's theory of general relativity tells us that time is not a fixed, universal constant ticking away at the same rate for everyone everywhere. Time passes differently depending on how strong the gravitational field around you is. The stronger the gravity, the slower time passes. This is called gravitational time dilation. And it is not just theoretical. The GPS satellites orbiting Earth have to correct for it. Time passes very slightly faster for them, up in their weaker gravitational field, and if they didn't account for this, their navigation calculations would drift and become inaccurate. Near a black hole's event horizon, this effect becomes almost impossible to comprehend in human terms. If you were watching a friend slowly descend toward a black hole's event horizon, watching from a safe distance, you would see something deeply strange. As they approached the event horizon, they would appear to slow down. Their movements would become more and more sluggish. The light reaching you from them would become redder and dimmer, and they would appear to freeze, essentially stopped at the event horizon, never quite crossing it, as time for them, from your perspective, slowed toward a stop. From your friend's perspective, time would feel perfectly normal. They would cross the horizon. They would continue falling. But the universe they left behind would be aging at a staggering rate relative to them. Time, near a black hole, is not what we are used to. It is something that warps and stretches and slows. Something more like a river that changes speed depending on the terrain it flows through. And if you crossed that horizon, if you fell in, something else would happen to you. Something that has been given a name almost too whimsical for the idea it describes. You would be spaghettified. Spaghettification is a genuine scientific term. It describes what the extreme gravitational gradient of a black hole would do to any extended object, including a human body, as it fell inward. Gravity from the black hole would be pulling on the parts of you closer to the center more strongly than on the parts farther away. Your feet, falling slightly ahead of your head, would be pulled harder. The difference in gravitational pull across the length of your body would stretch you, vertically, in the direction of your fall. And simultaneously, the same forces would squeeze you from the sides, narrowing you. Stretch and squeeze. Lengthened and thinned. Like dough being pulled into a long, fine strand of pasta. The point at which this becomes catastrophic depends enormously on the size of the black hole. Around a stellar mass black hole, small, as black holes go, the tidal forces become extreme quite quickly, and spaghettification would occur well before the event horizon. But around a truly supermassive black hole, millions or billions of times the mass of the Sun, the gradient across a human body would be gentle enough at the event horizon that you might cross it without feeling anything unusual. The universe, in its strangeness, offers a range of ways to fall. Some gentle, some not. Though of course, the destination is the same. Let your thoughts become very soft now, like something dissolving slowly in warm water. There is no need to hold on to anything firmly. Just let the ideas float through. In 1974, a physicist named Stephen Hawking sat down with the equations of quantum mechanics and general relativity, two theories that do not ordinarily play well together, and worked out something remarkable. Black holes are not entirely black. Quantum mechanics tells us that empty space is not truly empty. On the smallest scales, pairs of particles are constantly flickering into existence and annihilating each other, a sea of quantum fluctuation at the very fabric of reality. Ordinarily, these particle pairs appear and immediately destroy each other, leaving no net effect. But right at the edge of a black hole's event horizon, something different can happen. One particle of a pair falls in. The other escapes. The one that escapes carries energy away with it, energy that must come from somewhere. And what it comes from is the black hole itself. Over time, vast, almost incomprehensible spans of time, this process slowly drains the black hole of its mass. It radiates. Bit by bit, particle by particle, over trillions upon trillions of years, a black hole will shrink. And eventually, if nothing adds more mass to it, it will evaporate entirely, going out not with a roar, but with a final, tiny whisper of radiation. Hawking radiation is one of the most profound predictions in modern physics, a place where quantum mechanics and gravity briefly, delicately, touch. And it tells us that even the most permanent-seeming things in the universe carry within them the seeds of their own eventual ending. Brought with it a puzzle. A deep, troubling one that took physicists decades to wrestle with. If information falls into a black hole, the specific, detailed quantum information that describes exactly what every particle that crosses the event horizon is made of, and the black hole eventually evaporates, where does that information go? In quantum mechanics, information cannot simply cease to exist. It can be scrambled, hidden, transformed, but the total amount of information in a system must be conserved. This is a foundational principle of the theory. And yet a black hole, as originally described, seemed to swallow information and destroy it, releasing only featureless thermal radiation with no memory of what went in. This was called the black hole information paradox. And it troubled physicists enormously because it suggested that quantum mechanics and general relativity were not merely difficult to reconcile, they were fundamentally in conflict. Then, in 2020, a breakthrough. Physicists using new tools from quantum gravity were able to show, through careful calculation, that information is not destroyed. It is preserved, very slowly, very subtly, encoded into the Hawking radiation as the black hole evaporates. The information goes out the same way the energy does, scrambled almost beyond recognition. But there, nonetheless, it was a partial resolution. More work remains. But for the first time, there was a glimpse of how these two great pillars of physics might be reconciled. A thread connecting the quantum world and the world of gravity, found in the slow, patient evaporation of the universe's darkest objects. And finally, as we let this second act settle into stillness, one more idea. One more way of imagining what a black hole might truly be, at the deepest level. String theory is one of the most ambitious and controversial frameworks in modern physics, an attempt to describe all of the fundamental forces of nature in terms of tiny, one-dimensional objects called strings. Vibrating at different frequencies, these strings give rise to all the particles and forces we observe. And string theory has something unusual to say about black holes. Some physicists working within this framework have proposed that a black hole is not, at its heart, an empty void surrounding a singularity. Instead, they suggest that it might be a fuzzball, a dense, tangled mass of strings, filling the entire region that we would otherwise call the interior of the black hole, all the way out to where the event horizon would be. In this picture, there is no singularity, no point of infinite density where the laws of physics break down, and, crucially, no information paradox. Because the strings that make up the fuzzball remember, in their configurations and vibrations, everything that has ever fallen in. The information is not lost. It is woven into the structure of the fuzzball itself. This remains a hypothesis, an intriguing, mathematically active area of research, but not yet confirmed. The universe has not yet told us whether fuzzballs are real. But they are a reminder that our picture of a black hole, event horizon, singularity, emptiness, may itself be incomplete. That there may be a deeper layer of description, a richer and stranger picture, waiting to be found. The universe always has another layer. And tonight, we have only just begun to look. Rest now. Truly rest. You have thought about things tonight that the greatest minds in history spent lifetimes wrestling with. Let them sit gently in the back of your mind, like stones settling slowly to the bottom of a clear, still lake. Time bends near a black hole. Light loops in circles just beyond the edge of the dark. Even the most permanent things in the universe will, given enough time, evaporate into nothing. And somewhere, in the mathematics, in the vibrations of strings too small to ever see, the universe is keeping careful track of everything. Every particle, every bit of information. Nothing is truly lost. Carry that with you into Take a long, slow breath, in through the nose, and out through the mouth. Let your shoulders drop. Let your jaw unclench if it has been holding any tension. Let the space behind your eyes soften. You are here. You are still. And the universe is waiting patiently to show you something extraordinary. In our last chapter, we stepped close to the edge of a black hole. We stood at the event horizon and felt, in our imagination, the pull of something absolute. We watched time slow. We learned about light looping in perfect circles in the photon sphere, and about space being dragged like honey around a spinning cosmic giant. We met Stephen Hawking's quiet, astonishing prediction that even black holes eventually evaporate. And we ended with the strange possibility that what we call a black hole might, at the deepest level, be something stranger and richer still. Tonight, we step back. We take the widest possible view. Because there is another dimension to the story of black holes that is just as remarkable as their physics, and that is their sheer, staggering scale. Some things in the universe are not just large. They are large in a way that resists understanding. In a way that the human mind, shaped by evolution to navigate a world of trees and rivers and rooms, simply was not built to hold. We will try anyway. Gently, quietly, one astonishing fact at a time. Let your breathing deepen. Let the numbers we are about to encounter wash over you like waves, not to be grasped tightly, but to be felt. Our sun is not a small star. It contains more than 1,000,000 times the volume of Earth. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion. It has been doing this for nearly 5 billion years, and it will continue for another 5 billion more. By any human measure, it is an object of almost incomprehensible scale and energy. And now I would like you to imagine 66 billion of them. Not 66, not 600, 66 billion suns stacked together, each one 1,000,000 times the volume of Earth. The entire combined mass of 66 billion stars like our own, compressed into a single object. That object exists. It is called TON 618. It is a black hole located roughly 10.5 billion light-years from Earth, so distant that the light we observe from it left before our solar system had even formed. And its mass is 66 billion times that of the Sun, making it the most massive single object known to science. Its event horizon, the boundary from which nothing returns, is so vast that our entire solar system, from the Sun out to the distant edges of the Oort cloud, would fit inside it many times over. The distance from Earth to the Sun, a distance that light takes 8 minutes to cross, is a tiny fraction of TON 618's interior. If you were somehow placed at its event horizon, there would be nothing dramatic to see. No wall, no surface, just the same stars in every direction, and the slowly dawning realization from the mathematics of your position that every path forward led inward. 66 billion suns. One object. And it is not alone in its scale, it is simply the largest we have found so far. Now we go to the other end of the scale. From the largest to the smallest. From TON 618 and its 66 billion solar masses to something almost impossibly different. In 2019, astronomers identified what is thought to be one of the smallest black holes ever discovered. It contains approximately 3.8 times the mass of our Sun, so not a lightweight in ordinary terms, but at the very low end of the black hole spectrum. and its diameter is estimated at approximately 19 kilometers. 19 kilometers. The size of a mid-sized city. If you placed this black hole over city center, it would not even reach from one side of the metropolitan area to the other. You could, in a manner of speaking, walk its diameter in a few hours, if such a walk were not immediately fatal in ways that language struggles to adequately convey. 3.8 times the mass of the Sun, packed into 19 kilometers. Every atom of that mass, every particle, compressed into a sphere smaller than many of the towns and suburbs in which the people listening to this tonight might live. The density involved is a number so large that writing it out would require more digits than could comfortably fit on this page. The universe operates across ranges of scale that our intuitions were never designed to navigate. From black holes the size of a city to black holes larger than our solar system, and both of them obeying the same fundamental laws. Both of them curving space-time in the same fundamental way. Both of them utterly, absolutely dark. We tend to think of black holes as consumers, as devourers, things that take and do not give. But there is another way to think about them, as reservoirs of energy so immense that they dwarf everything else in the known universe. A spinning black hole carries within its rotation an almost unimaginable store of energy. As we discussed in our last chapter, every known black hole spins, some of them at extraordinary speeds. And that spin represents pure, stored energy. Not chemical energy, not nuclear energy, but the kinetic energy of mass rotating at a substantial fraction of the speed of light. For a maximally spinning black hole, up to 29% of its total mass can exist in this form, as pure rotational energy, in principle extractable. 29% of a mass that might be millions or billions of times that of the Sun, as usable energy. To put this in perspective, a star like our Sun converts about 0.7% of its mass into energy over its entire lifetime of fusion. A spinning black hole can contain, in rotational energy alone, more than 40 times that proportion of its mass. This makes black holes the most energy-dense objects in the known universe. Not despite their darkness. Not despite the fact that they produce no light of their own, but because of the sheer, extraordinary efficiency with which they store and, under the right conditions, can release the energy bound up in their rotation. The universe's darkest objects are also, in a very real sense, its most powerful batteries. And when a black hole feeds, when matter falls toward it and heats up in the process, the energy released can be almost beyond description. In the early universe, many supermassive black holes were actively consuming enormous quantities of gas and dust and infalling matter. As this material spiraled inward, it formed a vast, extremely hot disk around the black hole, heated by friction and gravitational compression to temperatures of millions of degrees. And that disk radiated light. Extraordinary quantities of light. The resulting structures are called quasars, quasi-stellar objects, and they are the most luminous persistent objects in the known universe. A single quasar can outshine 100 entire galaxies combined. Not 100 stars. 100 galaxies, each containing hundreds of billions of stars of their own. All of that combined starlight, outshone by the glow of a single black hole consuming matter at its center. And yet the black hole itself produces none of that light directly. The light comes from the material around it, heated to inconceivable temperatures by the process of falling in. The black hole is the engine. The infalling matter is the fuel. And the output is the brightest sustained light source the universe has ever produced. Many quasars we observe are so distant that their light has been traveling for most of the age of the universe to reach us. We see them as they were billions of years ago, in an earlier, more turbulent cosmic era. Most of the supermassive black holes in nearby galaxies today, including the one at the center of our own Milky Way, have quieted. Their fuel supply has dwindled. The great feast of the early universe is largely over. But for a brief window in cosmic time, they blazed. Let your body feel very heavy now. Pleasantly, comfortably heavy. Let each breath out carry a little more tension with it. The universe is vast, and you are here, resting, and the two facts sit together very peacefully. Black holes do not only consume, they also, sometimes, push back, with extraordinary force. When a supermassive black hole feeds voraciously, the magnetic fields and rotation of the system can focus some of that infalling energy into a pair of narrow beams, jets, fired outward from the poles of the black hole at nearly the speed of light. These relativistic jets are among the most energetic phenomena in the cosmos, shooting streams of charged particles thousands of light-years out into space. One of the most extreme examples ever recorded was associated with a galaxy designated SDSSJ 1106+ 1939. The black hole at its center launched an energy jet stretching over 1.5 million light-years into space. 1.5 million light-years. Our entire Milky Way galaxy, from edge to edge, spans roughly 100,000 light-years. This jet was 15 times longer than our entire galaxy. Its power exceeded the combined output of 2 trillion suns. 2 trillion. Not 2 billion. 2 trillion, a 2 followed by 12 zeros, suns, all burning at once, could not match the energy being poured into that single jet. These jets, where they intersect with the gas and dust of surrounding space, reshape the environments of entire galaxies. They heat gas that might otherwise cool and collapse into new stars, effectively regulating how quickly galaxies grow. Black holes, firing these jets, influence the fate of structure across millions of light-years. The darkest objects in the universe reach out, in this way, and shape the cosmos around them. Marks that last for millions of years. For most of human history, and for most of the history of modern astronomy, the supermassive black hole at the center of our own Milky Way was thought of as relatively quiet. Sagittarius A*, as it is called, seems sedate by quasar standards. It is not currently consuming large amounts of material. Its jets, if it has them now, are modest. But something in the structure of our galaxy told a different story. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered 2 enormous structures extending out from the center of the Milky Way, one above the galactic plane, one below. Vast bubbles of high-energy plasma, each stretching approximately 25,000 light-years. Together, they span 50,000 light-years, half the diameter of our entire galaxy. These are called the Fermi bubbles. They are the remnant signature of an event that happened millions of years ago, an eruption of Sagittarius A*, when the black hole at the center of our galaxy consumed something large enough to trigger an enormous outburst of energy. The plasma from that outburst expanded outward, and it is still expanding, still glowing in gamma rays, still visible to instruments sensitive enough to detect it. We live inside the echo of that ancient event. The Fermi bubbles extend into the space above and below us, enormous, ghostly, silent structures left behind by a black hole's outburst before our species existed. Before our genus existed. Before most of what we would recognize as modern life on this planet. Our galaxy carries its history written in structures of plasma, drifting slowly through the dark. The more we look, the more we find. And sometimes, what we find surprises us, not just by being large, but by being large in the wrong place. In 2025, astronomers announced the discovery of a black hole containing the mass of 17 billion suns. By itself, that number would be astonishing enough. 17 billion suns, in a single object. But it was not the mass that made this discovery remarkable to scientists. It was the location. This black hole was found in one of the most isolated, star-poor regions of the observable universe. A cosmic desert, a void largely empty of the galaxies, the dense stellar environments, the gravitational interactions and mergers that conventional models suggest are necessary for a supermassive black hole to grow to such a size. Our best understanding of how supermassive black holes grow to enormous masses involves a long process of mergers and feeding, galaxies colliding, bringing their central black holes together, triggering new waves of star formation and accretion. Rich environments, busy neighborhoods, cosmic abundance. And yet here was something with the mass of 17 billion suns, sitting alone in the quiet, in the desert. How it got there is not yet understood. Whether it grew in isolation, by some mechanism we have not yet identified, or whether it was somehow ejected from a richer environment long ago, the answer has not been found. It is a reminder that our models are maps, not territories. The universe is under no obligation to grow its black holes in the way we find most convenient to explain. Sometimes the most important discoveries are the ones that refuse to behave. You are doing so well. Let your thoughts grow quieter still. Like a sky after the last light has gone. Deep and dark and full of things you cannot quite see, but know are there. Nearly every large galaxy in the universe, every galaxy comparable in size to our own Milky Way or larger, appears to harbor a supermassive black hole at its very center. Not some of them. Nearly all of them. The universe, it seems, builds galaxies around black holes. Or builds black holes alongside galaxies. The relationship between the two, which came first, how they influence each other's growth, why they seem so intimately connected, is one of the most active areas of research in modern astronomy. The black hole at the center of our own galaxy is called Sagittarius A star. It contains approximately 4 million times the mass of the Sun. By the standards of supermassive black holes, it is quite modest, a quiet, relatively lightweight example. But it is ours. It sits at the heart of the galaxy in which every star we have ever seen with the naked eye resides. In which our Sun makes its slow orbit. In which our Earth travels through the dark. The discovery of Sagittarius A** and the careful confirmation of its mass through decades of observing the orbits of stars near the galactic center was awarded the Nobel Prize in Physics in 2020. Two astronomers, Andrea Ghez and Reinhard Genzel, shared that prize for the painstaking, decades-long work of watching those stars move. Each one of those stars, swinging around something invisible at the center of our galaxy, tracing orbits that could only be explained by an object of 4 million solar masses. Every orbit a data point. Every data point a quiet confirmation of something vast and dark and patient, sitting at the heart of our home. 4 million suns. And it is 26,000 light-years away from us. Close, by cosmic standards. Our own monster, at the center of our own galaxy. Settle around you like a blanket. Not pressing or heavy, just present. A reminder of context. Of how extraordinary the ordinary background of existence truly is. There is a black hole at the heart of the Milky Way. 17 billion solar mass black holes sit alone in the voids between galaxy clusters. Jets of energy stretch across distances 15 times the width of our galaxy. Fermi bubbles expand silently above and below us, the fading echo of an ancient eruption. And somewhere, 10 billion light-years away, Tuan 618 sits in the dark, 66 billion suns of mass, not burning, not shining, simply being. The universe is not a human-scaled place. It never has been. And yet we are here, small and warm and briefly conscious, with the extraordinary ability to reach out with mathematics and observation and discover these things. To know them. To name them. To let them gently reshape how we understand the vastness we inhabit. That is not a small thing. Rest now. Let the giants of the cosmos drift quietly through your mind as you move toward sleep. There is nothing to hold on to. Just the dark, and the knowledge that it is full of things more extraordinary than we were ever taught to expect. The story can Wherever you are right now, in bed, in a chair, drifting somewhere between waking and sleep, take a slow breath in and let it out. Let your body remember how to be heavy, how to be still. In our last chapter, we visited the giants. Ton 618, with its 66 billion solar masses. Jets stretching 1.5 million light-years through space. The Fermi bubbles, rising silently above and below our galaxy like the fading breath of an ancient eruption. We held the largest and smallest black holes side by side and felt the strangeness of a universe that operates across scales our minds were never quite built to contain. Tonight, we come home. Not all the way home. We are still talking about distances that would take tens of thousands of years to cross at the fastest speeds humanity has ever achieved. But closer. Closer to our corner of the cosmos, closer to our galaxy, to our neighborhood, to the dark things that share the Milky Way with us, moving through the same vast spiral of stars that contains our sun, our planets, and everything any human being has ever known. There is something different about closeness, even in astronomy. When we talk about a black hole 10 billion light-years away, the distance itself becomes a kind of buffer. It is too far to feel real. But when we talk about things in our own galaxy, things within the same structure we call home, something shifts slightly. The universe gets a little more personal. Let your breathing slow. Let your eyes close, if they haven't already. And let the Milky Way spread itself out above you in your imagination, that faint, familiar band of light, and know that it contains more than just stars. For most of human history, black holes were purely theoretical, mathematical objects. Things that lived in equations and thought experiments but had never been seen, could never be seen, many assumed, because the very nature of a black hole is that it emits no light. And then, slowly, that changed. The first image of a black hole was captured in 2019. The supermassive black hole at the center of the galaxy M87, 55 million light-years away. A glowing orange ring of superheated material surrounding a dark central shadow. It was one of the most celebrated scientific images ever produced, and it was achieved by synchronizing radio telescopes across the entire planet into a single Earth-sized instrument, the Event Horizon Telescope. But then, in 2022, something even more personal was achieved. Scientists turned that same planetary instrument toward the center of our own galaxy, toward Sagittarius A star, toward the black hole that sits at the heart of the Milky Way, our black hole. And they captured an image. It was the second image ever taken of a black hole, and in some ways the more difficult of the two. Sagittarius A** is far smaller than M87's central black hole, and the material around it moves so quickly that the image flickers and changes on timescales of minutes, requiring extraordinary techniques to combine thousands of images into a single coherent picture. But they did it. A glowing ring. A dark center. A photograph of something 26,000 light-years away, at the heart of our own galaxy, that had never been seen by human eyes before. We photographed our own monster, and it looked back at us, quietly, from the center of everything we have ever called home. Let that image rest gently in your mind. A ring of soft orange light. A circle of dark at its center. Now let us ask a quieter question. Of all the black holes we have found, detected, inferred, which one is closest to us? The answer, as best we currently know, is a black hole called Gaia BH1. It sits approximately 1500 to 1600 light-years away. Estimates have been refined over time, and a more careful measurement in 2023 using the Gemini North Telescope in Hawaii brought its distance into somewhat sharper focus. It lies in the direction of the constellation Ophiuchus, the serpent bearer, a constellation visible from most of the inhabited world on clear summer nights. Gaia BH1 is dormant. It is not feeding. It is not producing jets, or glowing in X-rays, or advertising its presence in any of the ways that make black holes detectable. It was found only because of its gravitational influence on a companion star, a normal, sun-like star orbiting this invisible object, its motion subtly but unmistakably tugged into an orbit that only made sense if something of roughly 3 solar masses was sitting at the center of that orbit, dark and silent. 1,500 light-years. Close, on a cosmic scale. So close that the light we see from the stars around it in the night sky left them only 1,500 years ago, in the early medieval period of human history. And at the other end of the scale, the most distant black hole yet detected sits approximately 13 billion light-years away, near the very dawn of the observable universe. Between these two extremes, 1,500 light-years and 13 billion, lies the full known range of black hole distances from Earth. We sit, as we so often do, somewhere quietly in the middle. Gaia BH1 is not the only black hole in our neighborhood. Not remotely. Our galaxy, the Milky Way, is estimated to contain somewhere in the range of 100 billion stars. Of those, a significant fraction are massive enough that when they die, they will leave behind black holes. Stellar mass black holes, formed from the collapsed cores of stars that exhausted their fuel and exploded. The current best estimates suggest that the Milky Way contains somewhere in the range of tens of millions of black holes. Some estimates go higher. All of them orbiting through the galaxy like invisible stars, following the same gravitational choreography as the visible matter around them, completing their slow orbits around the galactic center over timescales of hundreds of millions of years. Most of them are completely undetectable to us with current technology. A dormant black hole in the interstellar dark, not feeding, not close enough to any companion star to betray its presence gravitationally, is, for all practical purposes, invisible. It is simply there, moving, waiting, undiscovered. Tens of millions of them, sharing our galaxy with us. Scattered through the same spiral arms our sun inhabits. Moving through the same dark between the stars. The Milky Way is not simply a collection of stars and gas and dust. It is threaded through, in ways we are only beginning to map, with the dark remnants of stars that have lived and died across billions of years. The night sky we see, the handful of visible stars, the faint smear of the galactic plane, represents only the brightest, most visible fraction of what is actually out there. Now, something closer still. Not just the galaxy. Our solar system. Our particular small corner of the Milky Way. Our sun, along with everything that orbits it, all 8 planets, their moons, the asteroid belts, the distant comets, is making a slow orbit around the center of the Milky Way. It has been doing so since the solar system formed, nearly 5 billion years ago. It will continue for billions of years more. Each orbit takes roughly 230 million years to complete. And at the center of that orbit, exerting the gravitational influence that guides us along our path, is Sagittarius S star. Recent measurements have refined our understanding of exactly where we are and how fast we are moving relative to our galaxy's central black hole. Our solar system, it turns out, is traveling at approximately 227 kilometers per second. Every second, we are moving 227 kilometers. By the time you finish reading this sentence, we will have moved over 1,000 kilometers along our orbit. And we are approximately 25,800 light-years from the galactic center. Slightly closer and slightly faster than older estimates suggested. None of this poses any danger. The distances involved are so vast and our orbit so stable that Sagittarius A* exerts no meaningful influence on our day-to-day existence. It is simply there, 4 million solar masses of darkness, 26,000 light-years away, guiding us on our long, slow journey around the heart of the galaxy. We orbit a black hole. We have always orbited a black hole. The entire history of life on Earth has unfolded during the long, patient circuit of our solar system around that dark center. Let your breathing slow even further now. There is no need to hold on to the numbers. Just let the feeling of them remain. The sense of scale, of movement, of our small, bright solar system making its slow, reliable way around something vast and dark. Near the edge of Sagittarius A*, not close in human terms, but close in astronomical ones, something has been observed that adds another layer to our understanding of how black holes interact with the space around them. Magnetic fields. We have known for some time that magnetic fields exist near black holes. They are generated by the movement of charged particles in the hot, swirling material that surrounds actively feeding black holes. But around Sagittarius A*, even in its relative quiet, something striking has been found. The magnetic fields at the edge of our galaxy's central black hole are organized. They spiral outward in a precise, structured pattern, not the tangled, chaotic fields one might expect from a turbulent environment, but something deliberate seeming. Regular. Almost elegant. This discovery was significant not just for what it tells us about Sagittarius A* specifically, but for what it may tell us about black holes in general. The organized magnetic fields around our galactic center closely resemble those observed around the black hole in M87, the very first black hole ever imaged. Two very different black holes in two very different galaxies, showing the same structured magnetic behavior. This suggests that organized, spiral magnetic fields may be a universal feature of supermassive black holes. That these fields play a fundamental role in governing what falls in, what gets expelled, and how the black hole interacts with its surrounding galaxy. The invisible architecture of magnetism, spiraling outward from the edge of the dark. About the Fermi bubbles, those two enormous structures of high-energy plasma extending 25,000 light-years above and below the plane of our galaxy, discovered in 2010, left behind by an ancient eruption of Sagittarius A star. It is worth pausing with them a little longer, because they are not a distant phenomenon. They are ours. Right now, above and below the disk of the Milky Way, above and below the plane in which our solar system travels, those structures exist. They are expanding, slowly, into the space around our galaxy, glowing in gamma rays, enormous beyond easy description. And we did not know they were there until 15 years ago. For all of human history, for every civilization, every astronomer, every person who ever looked up at the night sky and tried to understand what they were seeing, those bubbles were there and invisible to us. Not because they are faint, in gamma-ray terms, but because we had not yet built the instruments to see them. Sagittarius A* erupted, millions of years before our species existed. The energy of that eruption expanded outward. It formed structures large enough to dwarf our galaxy's width. And it waited, patiently, for a civilization to develop the technology to finally notice. The universe does not announce its history. It simply holds it, encoded in structures of plasma and magnetism and light, until something comes along that is capable of reading it. We are only beginning to read it. Here is something that the mind wants to dismiss, but that is worth sitting with quietly. Because isolated black holes that are not feeding and not close enough to betray their presence through gravity are essentially invisible. Scientists have acknowledged that a wandering black hole could, in principle, pass through our solar system without our being aware of it. Not without any effect. A black hole moving through our solar system would warp the orbits of planets as it passed, bend the paths of comets, distort the trajectories of spacecraft. In principle, these effects would be detectable with sufficiently careful measurement. But in practice, particularly for a small, fast-moving black hole passing through without lingering, we might not notice until after it had already moved on. Or possibly not at all, if the perturbations were subtle enough. This is not a cause for alarm. The universe is extraordinarily empty. The distances between stars and between objects in interstellar space are so vast that the probability of any black hole coming near our solar system in the foreseeable future is vanishingly, almost incomprehensibly small. The same emptiness that makes them so hard to detect also makes a close encounter almost impossibly unlikely. But the possibility exists. Tens of millions of black holes moving through our galaxy on their own slow orbits. And space so vast that nearly all of them will spend their entire existence without coming meaningfully close to anything at all. Black holes, it turns out, are not fixed points. They are not anchored. They move through space exactly as stars and planets do, subject to gravity, participating in the grand gravitational choreography of the universe. And sometimes, something dramatic sends them moving very fast indeed. When two galaxies collide, and galaxies collide more often than you might expect, on cosmic timescales, the supermassive black holes at their centers can interact. They can orbit each other, as we discussed in our very first chapter. They can merge. And the merger, depending on how it unfolds, can send a recoil through space-time itself, a gravitational kick that flings the resulting black hole outward, away from the galactic center, at extraordinary speed. These are called runaway black holes, or rogue black holes, wanderers. And in 2025, observations revealed some of them hurtling through galaxies at speeds of up to 1,000 kilometers per second. Not orbiting, not settling, simply moving outward into the intergalactic void, carrying their mass and their darkness away from the structures that created them. One of the most striking examples was found using the James Webb Space Telescope. A runaway black hole, racing away from its home galaxy, had left behind it a trail, a contrail of compressed gas and newly triggered star formation, glowing in the wake of its passage. That trail stretched 200,000 light-years, longer than the entire width of the Milky Way. A black hole, moving through space so fast that it left a glowing scar in the universe behind it. A mark of its passage, written in newborn stars across 200,000 light-years of intergalactic space. The universe does not only create, it also flings. And the things it flings carry their strangeness with them, outward, into the dark. Let the images settle softly. A glowing ring of orange light at the heart of our galaxy. An invisible companion tugging a star into an unexpected orbit, 1,500 light-years away. Tens of millions of dark objects moving silently through the same spiral arms as our Sun. Magnetic fields spiraling outward from the edge of something ancient and enormous. Femi-bubbles expanding slowly above and below the galaxy we call home. And somewhere out in the intergalactic dark, a runaway black hole moving at 1,000 kilometers per second, trailing 200,000 light-years of glowing stars behind it like a comet's tail written on the largest possible scale. The universe is not distant and abstract. It is happening. Right now. In our galaxy. Around us. The darkness between the stars is not empty. It is full of things we are only learning to see. And you are here. Still. Breathing. Part of the same universe that contains all of this. Sleep. Settle in. Let your body find its most comfortable position, and then let it become just a little more comfortable still. Adjust anything that needs adjusting, and then let yourself become still. Take a breath in. Hold it gently for just a moment. And release. In our last chapter, we came home. We visited our own galaxy's black hole, photographed for the first time in 2022. We found the nearest known black hole to Earth, sitting quietly in the constellation Ophiuchus, betrayed only by its gravitational pull on a companion star. We learned that tens of millions of black holes share the Milky Way with us, invisible and patient, moving through the same dark between the same stars. And we ended with something vivid, a runaway black hole, ejected from its home galaxy, racing through intergalactic space at 1,000 kilometers per second, trailing 200,000 light-years of newborn stars behind it like a scar written across the face of the universe. Tonight, we watch the monster eat. Black holes, for all their stillness in our imagination, are not always quiet. When matter comes close enough, when gas or dust or the torn remnants of a star drift within reach, something extraordinary happens. The black hole feeds. And in feeding, it becomes one of the most energetic, luminous, violent environments in the known universe. Let your breathing slow. Let your mind become soft and receptive. And let us step close enough to watch. Imagine a vast, slow spiral. Not dramatic at first, more like water circling a drain, except the drain is an object of several million solar masses, and the water is clouds of gas stretching across light-years of space. As matter falls toward a black hole, it does not fall straight in. It has momentum, angular momentum, carried from whatever motion it had before it began its inward journey. And so it spirals, circling the black hole, drawing closer with each orbit, compressing, colliding with other infalling material. And as it compresses and collides, it heats. Not gently. The temperatures reached in the innermost regions of an accretion disk, the swirling disk of infalling matter that forms around a feeding black hole, reach tens of millions of degrees. Hotter than the interior of most stars. Hotter than almost anything else in the universe. At those temperatures, matter radiates. Powerfully. Primarily in X-rays, high-energy light that carries an enormous amount of energy per photon. The accretion disk of a feeding black hole blazes with X-ray light so intense that it can be detected from billions of light-years away. This is the great irony at the heart of black hole astronomy. The black hole itself is invisible, darkness absolute. But the material falling into it, heated by the process of its own destruction, becomes one of the brightest things in the universe. We find black holes not by seeing them, but by seeing the extraordinary light produced by everything around them in the moments before it disappears forever. The monster is dark, but its dinner glows. For a long time, astronomers wondered how supermassive black holes, objects containing billions of solar masses, manage to grow so large. Simply having matter nearby is not enough. Matter needs to lose its angular momentum, its tendency to keep orbiting rather than falling inward, before it can actually cross the final distance into the black hole. Something has to funnel it in. Astronomers using ALMA, the Atacama Large Millimeter Submillimeter Array, a collection of extraordinarily sensitive radio telescopes in the Chilean desert, made a discovery that helped answer this question. Near supermassive black holes, they found structures of magnetic, rotating wind. Vast, organized flows of magnetized gas, spiraling inward and downward toward the black hole in a pattern that resembles, on the most cosmic of scales, a tornado. These magnetic tornadoes actively transport matter. They carry gas inward, overcoming its tendency to simply orbit, funneling it toward the black hole where it joins the accretion disk and eventually falls in. They are, in effect, a feeding mechanism, a way the black hole reaches out into the surrounding space and draws its meal toward itself. This discovery helped explain one of the persistent puzzles of black hole growth. Not just where the mass comes from, but how it gets delivered. The answer, it turns out, involves magnetic fields doing something extraordinary, organizing the chaotic environment near a black hole into something almost structured. Almost deliberate. The universe, left to its own devices, finds ways to feed its darkest creations. Let your thoughts grow quieter. Let each breath come a little more slowly. The universe is patient. It has been building and feeding and growing its black holes for nearly 14 billion years. There is no hurry here. We have spoken about magnetic fields several times in our journey tonight. The organized spiral fields around Sagittarius A star. The magnetic tornadoes that feed supermassive black holes. And now, something that took the field of black hole physics by surprise as recently as 2025. Magnetic fields do not just influence how black holes feed. They influence what the black hole itself becomes from the very moment of its formation. New simulations completed in 2025 revealed something striking. When a massive star collapses to form a black hole, the strength of the magnetic field present during that collapse has a profound effect on the outcome. A strong magnetic field, it turns out, can slow the rotation of the forming black hole, carrying away angular momentum during the collapse itself. It can also carry away some of the mass that would otherwise have fallen in. The implication is remarkable. Two identical stars, the same mass, the same composition, the same internal structure, could, if they had different magnetic field strengths, produce very different black holes upon their deaths. One might produce a rapidly spinning black hole of a certain mass. The other, with a stronger magnetic field during collapse, might produce a slower spinning, lighter black hole. The magnetic field is not just a bystander. It is a sculptor. It shapes the black hole as it forms, determining not just whether a black hole is created, but what kind of black hole emerges from the collapsing star. The same stellar death, played out twice with different magnetic conditions, writes different endings. Now, something that broke into scientific news in early 2026, and that challenged assumptions that had stood for decades. There is a concept in black hole physics called the Eddington limit. Named for the astronomer Arthur Eddington, it describes a theoretical maximum rate at which a black hole can accrete, can feed. When a black hole consumes matter, the infalling material heats up and radiates. That radiation pushes outward on the surrounding gas. And at a certain feeding rate, the outward radiation pressure becomes strong enough to push the incoming gas away, effectively putting a ceiling on how fast the black hole can grow. The Eddington limit is not a hard physical law in the way that the speed of light is. It is more of a practical constraint, a point at which the black hole's own luminosity works against its ability to feed. But it has long been used as a guide for modeling how quickly black holes can grow. In January 2026, astronomers announced the discovery of a quasar from 12 billion years ago whose central black hole was accreting matter at 13 times the Eddington limit. Not slightly above. 13 times above. Consuming matter at a rate more than an order of magnitude beyond what the standard model suggests should be physically sustainable. This is not a small discrepancy. This is the universe doing something that, according to our best current models, it should not be able to do. And the fact that it appears to have happened 12 billion years ago, in the early universe, when many of the most puzzling aspects of black hole growth are concentrated, makes it all the more significant. How did it feed so fast? What mechanisms were at work? The answers are not yet known. But the question has been placed, clearly and urgently, on the table. The early universe holds many of the deepest puzzles in black hole science. And in recent years, our picture of how black holes grew in that distant era has shifted significantly. For a long time, the dominant model of black hole growth involved something relatively orderly. Matter falling steadily inward. Accretion proceeding at a measurable, manageable rate. Growth slow enough to be accounted for by the time available. But the supermassive black holes we observe in the very early universe, objects containing billions of solar masses, existing only a few 100 million years after the Big Bang, are too large. Too large for steady, orderly accretion to explain. There simply was not enough time, under the old models, for them to have grown that big. The emerging picture is messier, more chaotic. Black holes in the early universe, according to current thinking, did not grow through smooth, steady feeding. They grew through episodes, bursts, clumpy, irregular inflows of material, dense concentrations of gas falling in rapidly, followed by quieter periods, followed by another burst. A feast or famine model. Gorging when the conditions allowed, waiting when they didn't, then gorging again. This pattern of chaotic, episodic feeding can, in simulations, produce much faster overall growth than steady accretion. Fast enough, perhaps, to explain the giants we see so early in cosmic history. The early universe was a turbulent, dense, chaotic place. It should perhaps not surprise us that the black holes growing within it fed in a turbulent, dense, chaotic way of this directly. Among the many extraordinary discoveries made by JWST since it began science operations has been the identification of what astronomers have informally called the little red dots. They appear in deep field images of the early universe, small, red, compact sources of light that don't quite match the expected appearance of galaxies or known types of objects. Investigation has revealed them to be something remarkable. Extremely young black holes in the very early universe, feeding at extraordinary rates. Their red color comes partly from the rapid accretion itself, and partly from dust surrounding them, reddening their light in the same way that dust in our atmosphere reddens a sunset. These little red dots, which sounds almost charming as a name for some of the most extreme objects in the cosmos, are consuming matter at rates far beyond what existing models suggested was physically possible for black holes of their apparent age and mass. They are too big, too bright, too hungry for how young they are. They are not a small anomaly. There are many of them. And they suggest that the early universe was producing and feeding black holes through mechanisms we do not yet fully understand, mechanisms that allowed growth at rates our current models cannot adequately explain. Every deep field image JWST returns is full of them. Tiny, red, ancient, ravenous. Let your breathing deepen. Let the images drift. Tiny red points of light in the deep universe, each one hiding a black hole consuming matter faster than physics said it should. Let them be there, in their ancient sky, while you rest in your present one. In 2025, a different instrument, NASA's Chandra X-ray Observatory, one of the most sensitive X-ray telescopes ever launched, contributed its own piece to this puzzle. Chandra's observations, combined with careful modeling, revealed something about the black holes that grow more slowly, those that feed below the Eddington limit, at rates our models can accommodate more comfortably. For these black holes to grow from their initial formation into the supermassive giants we observe in the modern universe, within the time the universe has been in existence, they need to start large. Not just somewhat large. The calculations showed that black holes growing at or below the standard rate must have been born with masses of at least 10,000 times that of the Sun. Not 10,000 solar masses accumulated over time, 10,000 solar masses at birth. From the very beginning. This places a remarkable constraint on how the first black holes formed. The seeds were not small. They were enormous from the start, suggesting that the very first black holes did not form from individual collapsing stars, but from something larger. Denser concentrations of primordial gas collapsing directly, or from processes in the early universe that we have not yet fully identified. The constraints Chandra has placed on early black hole formation are, in a very real sense, a set of requirements that any successful theory of the early universe must meet. Whatever happened in those first few 100 million years, it produced black holes massive enough, from the very beginning, to grow into the giants we see today. The early universe was a black hole nursery, and the infants it produced were not small. Take a long, slow breath. Let it out completely. Let your body sink just a little further into rest. We have watched the monster feed tonight. We have seen matter spiral inward, heating to tens of millions of degrees, blazing with X-ray light. We have seen magnetic tornadoes funneling gas towards supermassive black holes across distances of light years. We have learned that magnetic fields shape black holes from the very moment of their birth, sculpting their mass and spin before they have even fully formed. We have watched a black hole from the ancient universe feeding at 13 times the rate our models said was possible. We have seen the little red dots, hundreds of them, scattered through the deep field images of JWST, each one a ravenous infant black hole from the universe's earliest days, consuming matter faster than we thought physics allowed. And we have learned that even the more orderly black holes among them needed to be born enormous, 10,000 solar masses at minimum, just to have enough time to grow into the giants we observe today. The universe is not gentle in its extremes. It does not observe its own speed limits. It does not always grow things in the ways our models suggest it should. It simply does what it does. Vast and dark and ancient. And we watch, with our telescopes and our equations and our slowly improving understanding, and we try to keep up. Sleep now. The monster will still be feeding when you wake. The little red dots will still be there in the deep universe, ancient and ravenous, waiting for us to understand them. There is more of the story to come. Rest well. Take a breath. A slow one. Let it fill you completely, and then let it go. Find your stillness. Whatever position you are in, let it be the right one. Let your body be heavy. Let your mind be soft. You don't need to hold on to anything tonight. Just let the words arrive, and let them drift through you like light through deep water. In our last chapter, we watched black holes feed. We saw matter spiraling inward, heating to temperatures no star can match, blazing with X-ray light even as the black hole itself remained invisible at the center. We met the magnetic tornadoes that funnel gas towards supermassive black holes across light years of space. We saw the little red dots, ancient, ravenous infant black holes from the universe's earliest days, feeding at rates that broke our models. And we learned that even the seeds of today's giants needed to be born enormous. Tonight, the universe turns up the energy considerably. This is the chapter of collisions. Of stars being torn apart, of neutron stars devoured, of black holes crashing into one another and sending ripples through the very fabric of space-time, ripples that pass through galaxies, through stars, through planets, through walls, through you, at this very moment, as you lie still and breathe. It is a violent chapter, but there is something calming about violence at this scale and distance. Violence so vast and so ancient that by the time it reaches us, it has become nothing more than a whisper. A gentle shiver in the geometry of space. A chirp, converted to sound, lasting less than a second. Let yourself be still. And let the cosmos be dramatic. Not every star dies in a supernova. Some meet a different end, stranger, in its way, and more violent. When a star wanders too close to a black hole, drawn gradually inward by the black hole's gravity, perhaps nudged by a gravitational interaction with another passing star, something extraordinary happens before it ever reaches the event horizon. The black hole's gravity does not pull equally on all parts of the star. It pulls more strongly on the side of the star that is closer, and less strongly on the side that is farther away. This difference, this gravitational gradient across the width of the star, is called a tidal force. And when a star gets close enough, the tidal force becomes stronger than the star's own self-gravity. Stronger than the force holding the star together. The star is torn apart. Not all at once, but in a cascade, material from the near side stretching toward the black hole, the star elongating, distorting, losing its shape. The outer layers stream away. The core follows. In a matter of days, a star that may have existed for billions of years is reduced to a long, glowing stream of debris, spiraling inward toward the black hole in a brilliant, flaring arc. This is called a tidal disruption event. And the flash of light it produces, The glow of stellar material being heated and consumed is detectable from billions of light years away. A star, in the process of its most extreme death, briefly outshines entire galaxies. The universe does not always end its stars quietly, but sometimes the death of a star by tidal disruption is stranger still. When the shredded debris of a torn-apart star begins its inward spiral, it does not always fall smoothly. Sometimes, in ways that astronomers are still working to fully understand, the debris does not form a clean, uniform stream. Instead, it clumps. It fragments. It collapses into a series of distinct, dense concentrations of material strung along the debris trail. Researchers at Harvard Center for Astrophysics, using observations across multiple wavelengths of light, confirmed a phenomenon that sounds almost too strange to be real. The shredded remains of a star, stretched out in a long arc around a black hole, can organize themselves into discrete clumps, evenly spaced, dense, glowing, like beads on a string. Each of those beads, in principle, might collapse into its own object. Not a star, not quite, something in between. The remains of a stellar death, fragmented into a series of dense mini-objects, strung along a glowing trail around the black hole that destroyed the star that made them. The universe, at its most violent, does not always produce simple outcomes. Sometimes it produces something that looks, to our instruments, almost decorative. A necklace of stellar debris, stretched around a black hole, each bead a piece of something that was once a star. It is one of those things that sits at the edge of what language can comfortably hold. Let the image of that necklace drift gently through your mind. Beads of light, strung around a dark center, and then let it soften. Let it blur at the edges. Stars are not the only things that fall victim to a black hole's appetite. Neutron stars, those extraordinarily dense stellar remnants we have encountered before in our journey, are among the most extreme objects in the universe in their own right. A teaspoon of neutron star material weighs billions of tons. Their magnetic fields are so intense that they would be lethal to ordinary matter at considerable distances. They are, in almost every sense, already at the limit of what matter can be while still being matter. And yet when a neutron star and a black hole find themselves in orbit around each other, a binary system, circling one another across a decreasing spiral, the black hole wins. As the two objects draw closer, the black hole's tidal forces begin to work on the neutron star in the same way they work on an ordinary star. The neutron star, extraordinary as it is, can be shredded. Its material, that almost incomprehensibly dense matter, is torn away and consumed. The collision that results is not quiet. It produces gravitational waves, sent outward through space-time at the speed of light in all directions. And it produces gamma-ray bursts, short, intense pulses of the highest energy light in the electromagnetic spectrum, so powerful that a single burst releases more energy in a fraction of a second than the sun will produce in its entire 10 billion year lifetime. Two of the most energetic phenomena in the known universe, happening simultaneously from a single violent event. The black hole always wins. But the neutron star goes out with extraordinary force. Now, something that was once thought impossible, and that was then observed. When two black holes merge, when they have been spiraling toward each other for millions or billions of years and finally collide, the event is, in terms of electromagnetic radiation, almost invisible. Black holes do not glow. They do not produce light when they collide. The merger sends out gravitational waves, but no flash, no fireball, no burst of radiation that optical telescopes could detect. Almost never. In rare circumstances, when two smaller black holes are not merging in open space, but are both embedded within the enormous gas disk surrounding a much larger supermassive black hole, the collision can interact with that surrounding gas in a way that produces light. The gravitational recoil from the merger can drive one of the resulting black holes through the disk, heating gas, triggering a brilliant flare of visible light. On May 21, 2019, the LIGO gravitational wave detector registered a signal, two black holes merging, sending their space-time ripples outward at the speed of light. And simultaneously, a telescope called the Zwicky Transient Facility, scanning the sky for flashes and flares, detected a burst of light from the same region of sky. A visible flare, coinciding with a gravitational wave signal. A merger, embedded in a gas disk, producing both a ripple in space-time and a flash of light that an optical telescope could see. For the first time, a black hole collision had produced something visible. A brief, brilliant signature, written simultaneously in two completely different kinds of signal, detectable by two completely different kinds of instrument. The universe offered us two ways to see the same event. And we had both instruments ready. Breathe slowly. Very slowly. Let your chest rise and fall without any effort at all. Let breathing be something that simply happens, without your direction. Gravitational waves. We have mentioned them several times on this journey, and now it is time to sit with them properly. When two massive objects, black holes, neutron stars, any sufficiently massive bodies, accelerate through space in orbit around each other, they disturb the fabric of space-time. Not dramatically, in most cases. The disturbance is there, but tiny, like the ripple from a pebble in an ocean. But when those objects are black holes, containing tens or hundreds of solar masses, and when they are in the final moments of an inspiral, moving at a significant fraction of the speed of light, separated by distances of only hundreds of kilometers, the ripple is no longer small. The disturbance propagates outward through space-time at the speed of light, passing through everything: gas clouds, stars, planets, the Earth itself, the walls of the room you are in, and through you, without interacting with any of it. Without being slowed, absorbed, or deflected. You cannot feel them. No instrument built on ordinary matter can sense most of them. But extraordinarily sensitive detectors, measuring the distance between mirrors with a precision far smaller than the diameter of a single proton, can detect the tiny stretching and squeezing of space as a gravitational wave passes through. We built those detectors. We called them LIGO, and Virgo, and Kagra. And they hear the universe in a way no telescope ever could. Wave signal from merging black holes was detected by LIGO in September 2015 and announced to the world in February 2016. It was one of the most celebrated scientific discoveries of the century. And when astronomers converted that signal into sound, mapping the frequency and amplitude of the gravitational wave into audible ranges, what they heard was this: a rising tone, a chirp. Beginning low, almost below hearing, rising quickly in pitch and volume as the two black holes approached each other, spiraling faster and faster, and then, a brief, sharp peak and silence. The chirp lasted less than a second. It represented the final fraction of a second of two black holes long in spiral, millions of years of slowly spiraling together, and then the very last moments, playing out in the time it takes to blink. In that fraction of a second, more energy was released in gravitational waves than the sun will radiate in its entire lifetime. The combined mass of the two black holes, each containing tens of solar masses, lost a small percentage of its total mass in the merger, converted directly into the energy of gravitational waves rippling outward through the universe. One brief chirp, and the cosmos changed what we knew about itself. LIGO has since detected black holes far more massive than initially expected, some up to 100 times the mass of the Sun, heavier than any stellar mass black hole our models had predicted could exist from the collapse of a single star. The universe, again, exceeding what we thought it was permitted to do. The gravitational wave detectors have not just expanded our knowledge. They have, on at least one occasion, confronted us with something that appeared, for a time, to be physically impossible. In 2023, the gravitational wave network detected a signal from a merger 7 billion light-years away. The black holes involved were extraordinarily massive, far beyond what existing models of stellar evolution suggested should be able to come together in a collision of this kind. The masses were too large. The event appeared to violate our understanding of how black holes of that size could form and find each other. For 2 years, it sat as an anomaly. A signal that was real, the detectors had seen it clearly, but that the models could not explain. Then, in late 2025, simulations from the Flatiron Institute provided a solution. Magnetic fields. The same magnetic fields we have encountered throughout our journey tonight, playing their role in star formation and black hole spin and accretion disk dynamics, here, playing a crucial role in the deaths of the massive stars that produced these black holes. Strong magnetic fields in the parent stars had altered the mass and spin of the black holes produced in their deaths, in ways that the earlier models had not accounted for. With magnetic fields properly included, the merger became possible. The physics held. An anomaly resolved. A signal finally explained. And magnetic fields, once again, sitting quietly at the center of the answer. And in 2025 itself, the gravitational wave detectors offered something even more extreme. A signal designated GW231123. Detected by the combined LIGO-Virgo-Kagra network, multiple detectors across multiple continents, all registering the same disturbance in spacetime within the time it takes light to travel between them. The signal came from the most massive black hole merger ever detected. 2 black holes, each of extraordinary mass, colliding and combining into something larger still. The combined mass of the system pushes against the theoretical upper limits of what stellar mass black holes born from the collapse of individual stars, are supposed to be able to produce. Above a certain mass range, stellar evolution models predict that a collapsing star should not produce a black hole at all. Instead, the explosion should be so complete that no remnant is left behind. This is called the pair instability mass gap. And the objects in GW231123 appear to sit in, or very near, that forbidden zone. How they got there is not yet fully understood. Perhaps they were themselves the products of earlier mergers. Perhaps the models of the mass gap need revision. Perhaps the universe has found yet another way to exceed what we thought were firm boundaries. The signal was real. The masses were measured. And the question of how they came to be sits, open and urgent, on the desks of physicists around the world. As our 6th chapter draws toward its close, something discovered as recently as March 2026. Something that added yet another unexpected shape to our catalogue of cosmic violence. Among the many gravitational wave signals detected by the network, one analysis revealed something unusual in the orbital geometry. A neutron star and a black hole, spiraling toward their eventual merger, this much was expected. Neutron star and black hole binaries had been detected before. But the orbit was wrong. Not circular, as binary systems of this kind are expected to be. Over long periods of time, gravitational wave emission carries energy away from a binary system, and that energy loss circularizes the orbit, gradually smoothing out any initial eccentricity into a near-perfect circle by the time the objects are close enough for the merger to be imminent. And yet this system had a distinctly elliptical orbit. Elongated. Oval. Eccentric in a way that should not have survived the long spiral to this point. The most likely explanation is that these 2 objects did not come together gradually, through the slow decay of a long-standing binary. They came together violently, through a dynamical encounter in a dense stellar environment, perhaps a globular cluster, where gravitational interactions between multiple objects can produce binaries with eccentric orbits on very short timescales. Not a partnership of billions of years, but a sudden, chaotic coupling. A neutron star and a black hole, thrown together by the violence of a dense stellar environment, still carrying in the shape of their orbit the memory of how they found each other. The gravitational wave signal told us not just that they were there, but how they came to be together. The shape of their orbit was a kind of history. Let that settle over you like quiet. The universe writes its history in shapes and signals and ripples in space-time. And we are learning, slowly, to read it. Tonight we have watched stars torn apart, their debris strung into necklaces of light around a dark center. We have heard the chirp of two black holes colliding, a sound lasting less than a second, representing millions of years of approach. We have seen a merger that seemed impossible, made possible by magnetic fields. We have met the most massive merger ever detected, pressing against the theoretical limits of what stellar mass black holes should be. And we have found a neutron star and a black hole in an oval orbit, carrying in the eccentricity of their path the fingerprint of a violent, chaotic origin. The cosmos is not still. It has never been still. It collides and tears and merges and sends ripples outward in every direction, and some of those ripples pass through you at this very moment, so gently that nothing in your body notices them at all. Let that be a comfort, in its strange way. The universe is immense and violent and ancient beyond imagining. And you are here, small and warm and breathing, and the ripples of its greatest collisions pass through you like whispers. Rest now. The story is not finished. But you have come a long way on this journey. We began at the very beginning, with the naming of black holes, with Einstein's reluctant equations, with the impossible density of the singularity. We watched black holes being born from dying stars and colliding neutron stars. We stepped close to the event horizon and felt time slow around us. We stood back and took in the giants, Turn 618 with its 66 billion solar masses, and the smallest black hole barely wider than a city. We came home to our own galaxy and found the monster at its center, quietly photographed for the first time only a few years ago. We watched the monster feed, and we watched it tear stars apart and collide with other black holes and send ripples through the fabric of space-time that pass through everything, including you, right now, as you lie still. Tonight, we take a step back from the drama. We ask a quieter question, a more human one. How did we find them? How does a civilization of small, warm, briefly living creatures on a rocky planet detect objects that emit no light, cannot be touched, and in many cases lie billions of light years away? How do you find something that is, by definition, invisible? The answer is one of the most remarkable stories in the history of science. And it is still being written. Black holes do not emit light. They do not reflect light. They absorb everything that reaches them, including every wavelength of the electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. Every kind of light we have ever invented a detector for passes into a black hole and does not come back. This means that no telescope of any kind, pointed in any direction, can directly image a black hole. The black hole itself will always appear as an absence, a shadow, a region of nothing, surrounded by something. And yet we have found hundreds of thousands of them. We have measured their masses with extraordinary precision. We have imaged the shadows they cast. We have heard the sound of two of them colliding. We have watched the orbits of stars around something invisible and calculated, from those orbits alone, that the invisible thing must contain 4 million times the mass of the Sun. We found them by looking at everything around them, by noticing what their presence does to light, to matter, to space-time itself, by becoming extraordinarily good at reading absence. The accretion disk around a feeding black hole blazes with X-ray light. We detect the disk and infer the black hole at its center. The stars near the center of our galaxy move in ways that only make sense if something massive and invisible sits at the point they orbit. We track the stars and infer what they orbit. Gravitational waves ripple outward from a merger. We measure the ripple and calculate the masses of the objects that produced it. Light from distant galaxies bends as it passes near a massive dark object. we map the bending and infer the mass causing it. Every method is indirect. Every detection is an inference. And every inference, built carefully on precise observation and rigorous mathematics, has proven reliable. We have become, as a species, extraordinarily skilled at finding things we cannot see. The most direct thing we have ever managed, the closest we have come to actually seeing a black hole, is the image produced by the Event Horizon Telescope. And even that is not an image of the black hole itself, but of its shadow. In 2019, the Event Horizon Telescope collaboration released the first image ever captured of a black hole's shadow, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. A glowing orange ring of superheated material, with a dark region at its center where the black hole's gravity prevents light from escaping toward us. Not the black hole itself, but the shape of its absence, outlined in light. To achieve this, astronomers synchronized radio telescopes across the entire surface of the Earth, in Chile, in Hawaii, in Spain, in Antarctica, in Arizona, into a single instrument with an effective aperture the size of our planet. The resolution required to image the shadow of M87's black hole from Earth is equivalent to reading the date on a coin in Los Angeles while standing in New York. And then, in 2022, a new technique was developed by researchers at Harvard Center for Astrophysics. Advanced computational algorithms, methods for extracting more information from the same raw data, for sharpening the image beyond what straightforward analysis could produce, were applied to Event Horizon Telescope observations. The result was dramatically sharper images of black hole shadows. Features that had been blurred and indistinct became clearer. The ring structure, the asymmetry of the glow, the precise shape of the shadow, all of it resolved with unprecedented clarity. We have been taking better and better pictures of something we cannot see. Each image a little sharper, each one revealing a little more of the shape of the dark. Let your eyes close a little more. Let the darkness behind them be comfortable. You are finding your way towards sleep, and the universe is finding its way towards sharper pictures of its own darkest places. Both of these things are happening at once. The next generation Event Horizon Telescope, the EHT, is already in development, and it represents a significant step beyond what has come before. The current Event Horizon Telescope uses only ground-based antennas. Even with telescopes spanning the full width of the Earth, the resolution achieved is at the limit of what a ground-based array can provide. To go further, to resolve finer structures, to capture more detail, you need a longer baseline. You need a telescope element that is farther away than any point on Earth's surface can be. You need to go to space. The EHT plans to incorporate space-based antennas, radio telescopes in orbit, extending the effective baseline of the array far beyond the diameter of Earth. And the goal is not simply sharper static images. The goal is motion. Real-time video of the region around a black hole, the accretion disk, the jet formation zone, the photon sphere, changing and evolving over minutes and hours. To see matter in the final moments before it crosses the event horizon. To watch the last light of infalling material as it approaches the point of no return. It will not be an image of the inside of a black hole. Nothing we build will ever show us that. But it will be the closest humanity has ever come, or likely ever will come, to watching the edge of the unknown in real time. The boundary between the knowable and the unknowable, rendered in radio waves, frame by frame. Not all detection methods require vast telescope arrays or space-based instruments. Some of the most elegant ways of finding black holes involve a kind of cosmic detective work, following unexpected clues wherever they lead. Stars, in dense stellar environments like globular clusters, interact gravitationally with each other constantly. The cluster is a busy place, stars passing close to each other, exchanging energy, sometimes forming binary systems and sometimes disrupting them. And occasionally, One of those gravitational interactions sends a star flying outward at extraordinary speed. A runaway star, ejected from the cluster by the gravitational slingshot of an encounter with something massive at the cluster's center. The thing that ejected it leaves a fingerprint. The direction of the runaway star, traced backward, points directly back to whatever flung it outward. Astronomers have used this technique to find hidden black holes sitting quietly at the centers of dense stellar clusters, invisible themselves, but betrayed by the trajectories of the stars they have thrown away. One such hidden black hole was revealed in the Large Magellanic Cloud, our galaxy's nearest large neighbor, by precisely this method. A runaway star, moving in a direction that made no sense unless something massive and dark was sitting at the point it had come from. The black hole did not announce itself, but it left its signature in the motion of what it had expelled. And that signature, read carefully by astronomers who knew what they were looking for, pointed unmistakably to the invisible. We find the unseen by following what it has touched. Breathe easily. Let your breathing be slow and automatic, something that happens without any thought. The universe is full of invisible things that leave traces in the visible. Your breathing is making traces too, in the warm air around you, in the slow rhythm of your chest. Everything leaves a mark. In March of 2025, a discovery was announced that significantly revised our picture of how many black holes the universe contains. Hundreds of previously unknown black holes were uncovered, not through some dramatic event or collision, but by a more patient process. These black holes had been hidden, concealed behind thick clouds of gas and dust that absorbed the X-ray light from their accretion disks, making them invisible to previous surveys. The clouds were, in effect, curtains, drawn across the black holes, leaving nothing visible behind them from Earth. New analysis techniques and new sensitivity in the instruments being used allowed astronomers to see through those curtains, to detect the signatures of black holes that had been there all along, simply obscured. And the implications were striking. If hundreds of previously undetected black holes could be found in a relatively small region of sky, the total population of hidden black holes across the observable universe could be vastly larger than current models predicted. Not millions, not billions, potentially trillions of black holes scattered throughout the cosmos, concealed behind clouds of gas and dust, invisible to all previous surveys. Trillions. The universe, it seems, has been hiding its darkest creations behind veils of dust, and we are only now beginning to learn how to look through them. Do not travel alone. Some exist in pairs, two supermassive black holes in the same galaxy, orbiting each other across a slow, vast gravitational waltz that will, in the fullness of cosmic time, end in merger. We have already spent time with the pair 9 billion light-years away, locked in their 2-year orbital dance, confirmed through 45 years of radio observations. But pairs of supermassive black holes have been found closer to home as well, or at least, closer in astronomical terms. Using the combined observing power of the Hubble Space Telescope and NASA's Chandra X-ray Observatory, optical and X-ray vision working together, each revealing what the other cannot, astronomers confirmed the existence of a supermassive black hole pair within a single galaxy. Two titans, each containing an enormous mass, orbiting each other in the same galactic core. This system is significant not just for what it is now, but for what it will eventually become. As the two black holes slowly lose energy through gravitational wave emission and dynamical interactions with surrounding stars and gas, their orbit will shrink. The waltz will speed up. And at some point in the deep future, millions or billions of years from now, they will merge. When they do, the gravitational wave signal produced will be unlike anything LIGO has ever detected. Supermassive black holes merging produce gravitational waves at much lower frequencies than stellar mass black holes, frequencies so low that they can only be detected by observing their effect on the regular pulses of distant pulsars, or eventually by space-based gravitational wave detectors that are already being planned. The merger of these two titans will send ripples across the entire observable universe. Gravitational waves powerful enough that, in principle, every pulsar in every galaxy within range will feel a tiny, synchronized shift in the timing of their pulses. A single event, leaving its mark on the whole of space. Let that settle into stillness. A single event, leaving its mark on everything. The universe is interconnected in ways that are easy to forget when we focus on individual objects, individual facts. But the gravitational waves that will one day emerge from that future merger are already, in a sense, promised. Built into the physics of those two orbiting giants, written into the future of the cosmos. We cannot see them yet, but we know they are coming. And this brings us, quietly, back to where we have been before. To the question of hidden things. To the question of what is out there that we have not yet found. The Chandra X-ray Observatory, in its patient, ongoing survey of the X-ray sky, has provided not just images and discoveries but constraints. Mathematical requirements. Things that must be true about the early universe, given what we observe today. We have touched on this before, and it bears sitting with again in this context of discovery. Certain black holes, Chandra's observations confirm, must have been born with masses of at least 10,000 solar masses, not grown to that size, but born at it, in order to have had enough time to grow into the supermassive giants we observe in the modern universe. The time available since the Big Bang is finite, and the growth rate of black holes, even feeding consistently, is bounded. Starting small, there is simply not enough time. So the seeds were large. The first black holes in the universe were not small, stellar mass objects. They were something else entirely, formed, perhaps, from the direct collapse of enormous primordial gas clouds, or from processes we have not yet fully identified. Something that produced 10,000 solar mass objects in the very first chapter of cosmic history. Chandra has given us a requirement. The universe must find a way to satisfy it. And working out how is one of the central challenges of modern cosmology. The telescope looked at the sky and came back with a constraint on the distant past. That is what good instruments do. They don't just show us what is there. They tell us what must have been. Let everything go soft. You have spent tonight in the company of people who spent their lives finding the invisible, who built instruments sensitive enough to detect the stretching of space by less than the width of a proton, who synchronized radio telescopes across an entire planet to photograph a shadow, who read the trajectory of a runaway star and traced it backward to the dark thing that had thrown it. They found what they were looking for, not because it was easy, because they were patient and precise, and unwilling to accept that the universe owed them a straightforward answer. It doesn't. But it leaves traces. It always leaves traces. Sleep well. One more chapter. You are close to the end of this journey now. Not quite there, but close. And perhaps that is reflected in where we are going tonight, because this final chapter of theory takes us to the very edges of what human thought has been able to reach, to the places where the equations become speculative, where the ideas are not yet confirmed and may never be, but where the mathematics is real and the questions are genuine and the possibility space is extraordinary. We have come a long way together. We named black holes and watched them be born. We stood at the event horizon and felt time slow. We met the giants and then came home to our own galaxy's quiet monster. We watched the monster feed and tear stars apart and collide with other black holes and send gravitational waves rippling outward through the fabric of everything. We learned how we found these invisible things, through shadows and ripples and runaway stars and the bent paths of ancient light. And now we ask the questions that do not yet have answers. The ones that sit at the frontier of human understanding, where the known gives way to the possible, and the possible gives way to the purely speculative but mathematically real. What are black holes, really, at the deepest level? Where does what falls in actually go? Could they connect to somewhere else? Does their opposite exist? And can we, on a laboratory bench on Earth, make something that behaves like one? Let your body sink into stillness. Let your breathing slow to something easy and deep. These are questions to carry into sleep, not to answer, but to hold gently, in the way that the best questions deserve to be held. The most romantic idea in all of black hole physics, the one that has captured the imagination of storytellers and scientists alike for decades, is the possibility that a black hole might be a doorway. Einstein's equations of general relativity, when examined carefully, permit a mathematical structure called an Einstein-Rosen bridge. A tunnel through space-time, narrow, curved, connecting one region of space to another. In principle, these bridges could connect two distant points in the same universe, or two different universes entirely. We call them wormholes, and they are a genuine, mathematically valid solution to the field equations of general relativity. And some physicists have wondered, could a black hole be the entrance to such a structure? Could whatever falls into a black hole emerge, somewhere else in space-time, through a corresponding white hole on the other side? The honest answer, from current physics, is almost certainly not. At least not in any way that would be useful, or survivable, or even detectable. Real black holes, the ones formed from collapsing stars, the ones we detect through gravitational waves and X-ray observations, are not, as best we can determine, traversable wormholes. The singularity at their centers is a genuine endpoint, not a junction. The geometry does not provide a passage through. Quantum effects would also destabilize any wormhole almost instantly after its formation, collapsing the tunnel before anything could pass through it. And yet the mathematical possibility remains. Einstein-Rosen bridges are real solutions to real equations. The universe does not always do everything its equations permit. But sometimes it does. And the wormhole sits there in the mathematics, a door that the laws of physics may have locked from the inside. We press our ear against it and hear nothing. But we have not stopped wondering what might be on the other side. And if a black hole is a region that only takes in, that absorbs everything and releases nothing, then general relativity, applied with mathematical care, suggests that something should exist which does the opposite. A white hole. A white hole is, in the most literal mathematical sense, the time reversal of a black hole. Where a black hole has an event horizon that matter can cross only inward, a boundary you can enter but never exit, a white hole has a boundary that matter can cross only outward. Nothing can fall into a white hole. Everything is expelled from it. Light, matter, radiation, all of it pushed outward, away from the white hole's interior, which cannot be reached by anything from outside. It is the opposite of a black hole in every operational sense. And it is a perfectly valid solution to Einstein's field equations. No white hole has ever been observed. Almost no physicist seriously expects one to be found. The conditions required for a white hole to form naturally seem to be absent from the universe as we know it, and thermodynamic arguments suggest they would be extraordinarily unstable even if they did form. The universe appears to strongly prefer the direction of time in which things fall in rather than fly out. But here is what is worth carrying quietly into sleep. The equations do not forbid them. General relativity, the most precisely tested theory in the history of physics, looks at white holes and says, this is allowed. This is consistent with everything I describe. I find no contradiction here. The universe has not made them, as far as we can tell. But it could have. And perhaps, somewhere in the vast space of possibilities we have not yet examined, it did. Let your thoughts grow soft and slow, like something dissolving at the edges. You don't need to hold on to any of this tightly. Just let it drift. At the center of a black hole sits the singularity, that point of infinite density where our equations break down and produce nonsense answers. It is, as we discussed in our very first chapter, the edge of what current physics can describe. The place where the map runs out. But maps can be redrawn. And in 2026, a new theoretical proposal was put forward that suggests the singularity might not be the final answer, that what we call a black hole might not actually contain a singularity at all. The proposal describes what its authors call dark stars. Not a black hole in the traditional sense, not a region of pure collapsed spacetime surrounding a point of infinite density, but instead an extraordinarily dense object made of exotic matter, compacted to a size that makes it indistinguishable from a black hole to anything observing it from outside. From the outside, a dark star would look exactly like a black hole. It would have an event horizon. It would bend light in the same way. It would affect the orbits of surrounding stars identically. No external observation could tell the difference. But inside, rather than an empty void collapsing to a singularity, there would be structure. A real interior, made of real, if extraordinarily exotic, matter. No infinite density. No breakdown of physics. Just something we do not yet have a complete theory to describe, but which avoids the catastrophic failure of our equations that the singularity represents. If dark stars are real, the singularity problem, one of the longest-standing crises in theoretical physics, dissolves. Not because we found the deeper theory that replaces general relativity, but because the singularity was never there to begin with. The universe, in this picture, found a way to avoid it. The idea is new. It is not confirmed. It may never be. Distinguishing a dark star from a true black hole observationally, given that they look identical from outside, would be extraordinarily challenging. But the mathematics is real. And the motivation for pursuing it, removing the singularity from our picture of black holes, is one of the deepest motivations in all of theoretical physics. We have met dark matter several times on this journey. That invisible substance, making up most of the matter in the universe, detectable only through its gravitational effects, never directly observed, is one of the deepest unresolved mysteries in modern physics. And some cosmologists have proposed that the two great mysteries of modern astrophysics, dark matter and the origin of supermassive black holes, might be connected. Not just related, but the same thing, viewed from different angles. The proposal is for a category of black holes formed not from the collapse of ordinary matter, not from dying stars or colliding neutron stars or infalling gas, but from dense concentrations of dark matter in the early universe. Regions where dark matter was packed tightly enough that it collapsed under its own gravity, forming black holes from something we have never directly detected, producing objects we have never confirmed. Dark matter black holes. A category that, if it exists, would represent the first direct physical link ever established between dark matter and black hole physics. Two of the deepest puzzles in science, connected at their roots. They have not been found. They may not exist. But if they do, they would be out there, drifting through the early universe and the modern one, formed from invisible matter, themselves invisible, carrying in their existence the answer to questions that have troubled physics for generations. The universe may have organized its mysteries into a single object that solves two problems at once. It has done stranger things. String theory, the framework that describes all fundamental particles and forces as the vibrations of tiny one-dimensional strings of energy, makes a striking proposal about what a black hole actually is. Or more precisely, what it is not. In the fuzzball picture, developed by string theorists over many years, a black hole is not an empty void surrounding a singularity. It is not a region of collapsed spacetime with an interior of nothingness. It is a dense, tangled, seething mass of strings, filling the entire volume that we would otherwise call the interior of the black hole, right out to where the event horizon would be. A fuzzball has no interior vacuum, no singularity, no point where physics breaks down, and crucially, it has no information paradox, because the strings that fill the fuzzball remember everything. Every particle that has ever fallen into the black hole has left its imprint on the configuration of strings within. The information is not lost. It is encoded in the fuzz. From outside, a fuzzball looks exactly like a black hole. The same shadow, the same gravitational effects, the same absence of any outgoing light. But the interior is not empty. It is full of the vibrating strings that string theory proposes underlie all of physical reality. This remains theoretical. String theory itself remains unconfirmed by experiment. But the fuzzball is not a frivolous idea. It is a serious, mathematically developed proposal that addresses real problems in a real framework. The black hole, in this picture, is not a void. It is a knot. Rest quietly. A knot of strings, filling the dark. Everything that ever fell in, still there, encoded in vibration. Now, a story about a bet. A very famous one, between some of the most formidable minds in late 20th century physics. In 1997, Stephen Hawking and Kip Thorne, both giants of theoretical physics, Hawking famous for his work on black holes and Thorne for his on gravitational waves, made a formal wager against John Preskill, a theoretical physicist at Caltech known for his work in quantum information theory. The subject of the bet was the black hole information paradox. Hawking and Thorne argued that information falling into a black hole was genuinely, permanently lost. That the universe, at the level of black hole physics, did not preserve quantum information, that what went in was gone, and the thermal radiation that eventually came out contained no memory of it. Preskill argued the opposite. That quantum mechanics, which requires information to be conserved, must win. That somehow, in ways not yet fully understood, the information must be preserved. 7 years later, in 2004, Hawking stood up at a scientific conference and conceded the bet. He had become convinced, through new calculations using approaches from string theory and quantum gravity, that information was likely preserved after all, that it leaked back out, subtly encoded in the Hawking radiation, over the immense timescale of the black hole's evaporation. He presented Preskill with an encyclopedia, the agreed-upon prize, from which information could be retrieved at will. A small, dry joke from a man who had just publicly reversed one of his most deeply held theoretical positions. Kip Thorne, it should be noted, did not concede. He remained unconvinced that the question was settled. The bet is remembered not just as a story about Hawking's intellectual honesty and flexibility, remarkable qualities in any scientist, extraordinary in one of his stature, but as a marker in the history of the information paradox. A public moment when the debate shifted, when the weight of evidence and argument moved, visibly, from one side to the other. The paradox is not fully resolved, but the direction of travel has changed. And finally, something that brings all of this extraordinary theoretical physics down to earth. Literally. Hawking radiation is one of the most important predictions in modern physics. It connects quantum mechanics and general relativity in a delicate, precise way. But it has never been directly detected. Real black holes radiate so feebly, the temperature of Hawking radiation from a stellar mass black hole is so unimaginably small that no instrument we could conceivably build would be sensitive enough to detect it. The signal is there, in principle, but it is far, far beyond our current ability to measure. Unless we don't use a real black hole. Physicists have discovered that the equations governing the behavior of sound waves in certain fluids, specifically fluids moving faster than the speed of sound, are mathematically identical to the equations governing light near a black hole's event horizon. Sound in a supersonic fluid behaves, in the relevant mathematical sense, exactly like light near a black hole. This means you can make a sonic black hole, an acoustic black hole, a region in a laboratory fluid, or in a Bose-Einstein condensate, a strange state of matter that exists only at temperatures close to absolute zero, where the flow of the fluid is fast enough that sound waves cannot propagate against the current. A sonic event horizon. Sound that goes in cannot come back out. And in these laboratory systems, physicists have detected what is mathematically analogous to Hawking radiation. Acoustic phonons, quantum units of sound, produced at the sonic event horizon, carrying energy away from the acoustic black hole in a pattern that matches Hawking's predictions precisely. It is not the same as detecting real Hawking radiation from a real black hole. The underlying physics is different at the deepest level, but the mathematical analogy is exact. And the detection of the acoustic equivalent is strong evidence that Hawking's theoretical framework is correct, that the mechanism he described really does produce radiation at event horizons, even if we cannot yet test it on the real thing. We built a black hole in a laboratory, not of space-time and collapsed matter, but of cold fluid and sound. And it behaved exactly as the theory predicted. The universe, generous in its mathematical structure, gave us a way to test the untestable. We took it. Edges of the map. We have traveled, in this journey, from the naming of black holes to their formation, from their extremes of size to their feeding and violence, from the methods we use to find them to the theories we are still building to understand them. We have stood at the event horizon, in imagination, and felt time slow. We have heard the chirp of colliding black holes, converted to sound. We have watched the universe hide its darkest creations behind clouds of dust, and watched us learn to see through the dust. We have sat with the questions that don't have answers yet. Wormholes that probably aren't. White holes that mathematically are. Dark stars that might replace the singularity. Dark matter black holes that might connect two great mysteries into one. Fuzzballs made of vibrating strings that might preserve everything that ever fell in. A famous bet, conceded gracefully, marking a turning point in one of the deepest debates in physics. And laboratory black holes, made of cold sound, confirming in analogy what we cannot yet test in reality. This is where the science lives right now. Not in the comfortable certainties, but in the frontier. In the places where multiple serious proposals exist and none has yet been confirmed. Where the next generation of telescopes and detectors and theoretical physicists will spend their careers. The story of black holes is not finished. It has barely begun, in some respects. We have been studying them seriously for less than a century. We have been detecting them directly for only a decade. The greatest discoveries about the universe's darkest objects are almost certainly still ahead. You have come to the end of the journey, or perhaps the end of this part of it, because the universe's story does not end, and neither does our attempt to understand it. Let everything you have heard tonight settle softly. You don't need to remember all of it. You don't need to hold on to any particular fact. What matters is the feeling. The sense of a universe that is incomprehensibly vast and strange and full of things that bend the mind and defy easy imagining. A universe that creates monsters and hides them, that keeps records in Hawking radiation and ripples in space-time and the trajectories of runaway stars, that permits wormholes in its mathematics and white holes in its equations and fuzzballs in its string theory, and that waits patiently for the brief, curious creatures on one small planet to develop the instruments and the mathematics to find them. We are those creatures, and we have found so much. Let your breathing slow to its nighttime rhythm. Let the weight of your body be entirely supported by whatever holds you. Let the thoughts grow quiet and formless, the way thoughts do at the edge of sleep. The black holes are out there. Ton 618, 66 billion solar masses, 10 billion light-years away. Sagittarius A*, 4 million solar masses, at the heart of the galaxy in which you exist. Gaia BH1, quiet and dormant, 1500 light-years away in Ophiuchus. The runaway black hole, trailing 200,000 light-years of newborn stars. The little red dots, ancient and ravenous, in the deep field images of the James Webb Space Telescope. All of them there. All of them real. All of them sharing a universe with you. Sleep well. The cosmos is vast and extraordinary and deeply, peacefully indifferent to your worries. Let it hold you for a while. Take a breath. A slow, deep one. Let it fill you completely, and then let it go all the way until your lungs are empty and quiet. And then breathe again, without effort. Let your body do what it knows how to do. You have been on a long journey. And tonight we arrive at something that sits at the very heart of the black hole story, not the physics of individual black holes, remarkable as that is, but the bigger picture. The question of how the universe itself was shaped by these objects. How the largest structures in the cosmos, the galaxies, the galaxy clusters, the great web of matter stretching across billions of light-years, came to be what they are, and what role black holes played in making them. We are going back in time tonight. Back to the early universe. Back to an era so distant that the light from it has been traveling for most of the age of the cosmos to reach us. An era when the universe was young and dense and turbulent and full of processes we are only now beginning to understand. The questions we are asking in this chapter are among the deepest in modern astrophysics. They are not fully answered. Some of them may not be answered in our lifetimes. But the outlines of answers are beginning to emerge from the James Webb Space Telescope, from the Chandra X-ray Observatory, from gravitational wave detectors, from supercomputer simulations running for months to model events that happened billions of years ago. Let your body be heavy. Let your mind be open. And let the early universe spread itself out around you in the dark. There is a question that sits at the center of modern astrophysics like a stone at the center of a still pond, sending ripples outward into every adjacent field of study. It is a question that sounds deceptively simple, and that turns out to be extraordinarily difficult to answer. How did supermassive black holes form? We know they exist. We have imaged one. We have detected the gravitational waves from black hole mergers. We have observed quasars, the blazing signatures of supermassive black holes feeding in the early universe, at distances so great that the light we see from them left before our solar system existed. But we do not know, with any confidence, how black holes went from whatever they were at the beginning to what we observe today. Were they born massive, formed in the first moments of cosmic history through some process that produced objects of thousands or millions of solar masses directly? Or did they begin small, as stellar mass black holes, formed from the first generation of dying stars, and grow over billions of years by consuming matter and merging with each other? Or was it some combination? Different black holes following different paths to their eventual sizes, some beginning large and some beginning small, the universe finding more than one route to the same destination? The answer to this question would not just tell us about black holes. It would tell us about galaxy formation, about why galaxies are the sizes they are, why they have the structures they do, why the supermassive black hole at a galaxy's center seems so tightly connected to the properties of the galaxy around it. Understanding black hole origins may be the key to understanding why the cosmos looks the way it does. It is one of the great open questions. And the universe has been giving us pieces of the answer, slowly, through our most powerful instruments. We have encountered the impossible merger before. In our chapter on cosmic violence, we briefly met the collision detected in 2023 between two black holes so massive that the merger seemed to violate our existing models. But it deserves more time now, because of what it tells us about the early universe and how black holes grow. The merger was detected 7 billion light-years away. 7 billion light-years, meaning it happened 7 billion years ago, when the universe was roughly half its current age. The two black holes involved were far more massive than standard stellar evolution models predict a single collapsing star can produce. Under our best understanding of how massive stars live and die, there is a mass range, a gap, where the explosion of a dying star should be so complete that no remnant is left behind. No neutron star, no black hole, just dispersed stellar material. And yet here were two black holes sitting in, or very near, that forbidden mass range. Objects that, according to the models, should not have been able to form from single stellar collapses. For 2 years, the merger sat as an anomaly. Real, the detectors had measured it clearly, but unexplained. The resolution came in late 2025 from simulations run at the Flatiron Institute. And the answer was magnetic fields. As we have seen repeatedly throughout this journey, magnetic fields play a deeper and more varied role in black hole physics than was previously appreciated. In the parent stars of these black holes, strong magnetic fields during the final stages of stellar evolution had altered the mass and spin of the black holes produced. The same stars, without those magnetic fields, would have produced black holes of different masses, masses that would have fallen neatly within expected ranges. With the magnetic fields included, the merger became possible. The anomaly dissolved. The physics held. And the lesson, once again, is the same one we keep learning. The universe is more magnetically complicated than our simpler models assumed. Magnetic fields are not a secondary effect to be added after the main physics is understood. They are woven into the main physics from the beginning. Let your breathing slow. Let each breath be a little longer than the last. You are drifting toward sleep, and the early universe is drifting toward the beginning of time. Both journeys, in their way, move toward something quiet and fundamental. Among the most luminous objects in the known universe are quasars, the blazing accretion disks surrounding supermassive black holes in active feeding frenzies. We have met them before. A single quasar can outshine 100 entire galaxies combined, powered entirely by the gravitational energy of matter spiraling into the black hole at its center. And many of the most powerful quasars we observe are ancient. Their light has been traveling for 10, 11, 12 billion years to reach us. We see them as they were in the early universe, in the first few billion years after the Big Bang, when the cosmos was denser and more turbulent and the supply of infalling gas was, in many regions, vastly more abundant than it is today. These ancient quasars pose a profound puzzle. For a supermassive black hole to be powering a quasar at that luminosity, that early in cosmic history, it must already contain billions of solar masses. It must have grown to an enormous size in what is, cosmically speaking, a very short time. How? The universe was young. The time available for growth was limited. And our standard models of black hole growth, steady accretion, orderly feeding, gradual accumulation of mass, cannot, when the numbers are worked through carefully, get a black hole to billions of solar masses in the time available. Something else must have been happening. Something faster. Something more extreme. And the answer that is emerging from recent simulations and observations is not a comfortable, orderly one. It is chaos. The picture that has been assembling itself, piece by piece, from observations by the James Webb Space Telescope and from sophisticated computer simulations, is one of dramatic, episodic, wildly irregular growth. Black holes in the early universe did not grow by steadily sipping from a smooth, continuous flow of infalling matter. They grew by gorging. By consuming enormous clumps of dense gas in violent, brief episodes, matter falling in not as a gentle stream but as irregular, clumpy bursts, each one delivering far more mass in a short time than steady accretion could account for. Between these episodes of violent feeding, the black hole would quieten. The available dense gas would be consumed or pushed away. And then the conditions would change again, another dense concentration of matter would fall within reach, and the black hole would gorge again. Feast and famine. Gorge and wait. Gorge again. This chaotic, episodic model of early black hole growth can, in simulations, produce black holes of the masses we observe in the early universe within the time available. The chaos is not a bug in the story. The chaos is the mechanism. The violence of the early universe, its turbulence, its density fluctuations, its irregular and lumpy distribution of matter, was precisely what allowed black holes to grow so fast. The universe, in its youth, was not a calm place. And the black holes that grew within it were not calm either. They were products of their environment, shaped by the turbulence around them, growing in fits and starts, feasting when they could, waiting when they had to, and emerging from that chaotic early era as the giants we observe today. And into that chaotic early universe, the James Webb Space Telescope has been staring with extraordinary sensitivity, looking at the deep universe, at regions of sky where the light arriving at our detectors left its source 10, 11, 12 billion years ago, and finding things that were not expected. The little red dots. We have met them before, in our feeding chapter. But here, in the context of cosmic history, they take on a different significance. These compact, reddish sources of light, scattered through the deep field images of JWST, are black holes. Extraordinarily young ones, in cosmic terms. Existing only a few 100 million years after the Big Bang, in the earliest chapter of the universe's story. And they are feeding rapidly, at rates that, according to the models we had before JWST began its observations, should not have been physically possible for black holes of their apparent age and mass. They are too big, too bright, too hungry, too early. Not one or two of them, an anomaly to be set aside. Hundreds of them, scattered through deep field after deep field. A population of objects that are systematically inconsistent with our pre-existing models of how black holes form and grow in the early universe. They are telling us something. Loudly, clearly, in red light from the dawn of the cosmos. They are telling us that whatever process created and fed the first black holes in the universe was different, faster, more extreme, less constrained than we thought. X-ray Observatory has been adding its own constraints to this story. Quietly, precisely, in the way that X-ray telescopes do. We have returned to this finding several times throughout our journey, because it is important enough to revisit, and here, in the chapter of cosmic history, it fits most naturally. Chandra's observations have established something that functions as a firm requirement on the early universe. 4 black holes growing at or below the standard Eddington rate, feeding at or below the theoretical maximum, to have reached the sizes of the supermassive giants we observe today within the age of the universe, they must have started large. Very large. At least 10,000 solar masses at birth, and possibly much larger. This is not a small seed. 10,000 solar masses is not what you get from a single collapsing star. The most massive stars we know of contain perhaps a few hundred solar masses, and they do not convert all of that mass into a black hole when they die. 10,000 solar masses requires something different. A direct collapse, an enormous cloud of primordial gas, perhaps containing millions of solar masses, collapsing directly into a black hole without first forming a star. Or a very rapid succession of mergers in a dense, early stellar environment. Or something we have not yet imagined. Whatever the mechanism, the requirement is clear. The seeds were not small. The first black holes in the universe were already large, extraordinarily large, at the moment of their formation. And the universe somehow produced them, in its first few 100 million years, through processes we are still working to identify. And then there is the darkest possibility of all. The one that sits at the intersection of 2 great mysteries. Dark matter remains the deepest unsolved problem in observational cosmology. We know it is there, The evidence from galaxy rotation curves, from gravitational lensing, from the large-scale structure of the universe is overwhelming. Something with mass, something that interacts gravitationally with ordinary matter, is present in enormous quantities throughout the cosmos, in a ratio of roughly 5:1 compared to ordinary matter. But we have never detected it directly. Every experiment designed to catch dark matter particles in a detector has come up empty. Every candidate particle predicted by extensions of the Standard Model has failed to appear where our models suggested it should. Some cosmologists have proposed that part of the answer to both mysteries, the nature of dark matter and the origin of supermassive black holes, might be the same object. Dense concentrations of dark matter in the early universe, collapsing under their own gravity, could have formed black holes, not from ordinary matter, but from whatever dark matter is made of. These dark matter black holes would have formed before the first stars. Before the first ordinary matter had had time to cool and collapse into stellar nurseries. They would have been present in the early universe as seeds, large seeds, potentially, around which ordinary matter could later accumulate, helping to explain both the rapid growth of early supermassive black holes and the apparent ubiquity of dark matter in galactic structures. If they exist, they solve two problems simultaneously. They give us the seeds we need for early black hole growth. And they give dark matter a place to go, a form it can take that is consistent with all the gravitational evidence without requiring a new particle to be detected. It is speculative. It is not confirmed. The evidence for dark matter black holes specifically, as distinct from dark matter in other forms, does not yet exist. But the idea sits at the junction of the two deepest mysteries in modern astrophysics. And in science, when two unsolved problems point toward the same possible solution, that is always worth taking seriously. Let your mind grow very quiet now. Very still. We have been to the edge of the observable universe tonight, and to the beginning of time. We have watched the first black holes forming from impossible seeds in a turbulent, chaotic infant cosmos. We have watched them grow through violent feasting, through magnetic fields we are only beginning to account for, through processes that broke our models and required us to rebuild them. We have met the little red dots, hundreds of them, ancient and ravenous, staring back at us from the first chapter of the universe's story, insisting that something we thought we understood about black hole growth is not quite right. The seeds of today's giants must have been enormous. That the early universe must have found a way to produce black holes of at least 10,000 solar masses before it had even had time to form most of its stars. And we have touched the possibility, speculative, unconfirmed, but serious, that dark matter and the origin of black holes might be the same story. That the universe's two deepest mysteries might be reflections of each other, seen from different angles, waiting to be recognized as one. These are the questions that the next generation of astronomers will spend their careers on. The answers are not here yet. But the instruments are being built. The simulations are being run. The data is being gathered by telescopes that can see further back in time than any instrument in human history. The early universe is not a closed book. It is a book that is being read slowly and carefully, one extraordinary page at a time. You have been on a long journey. 9 chapters now. From the naming of black holes to their birth, from their physics to their scale, from our galaxy to the edge of the observable universe, from the violence of collisions to the theory of fuzzballs, from the methods of detection to the mysteries of the very first moments of cosmic time. And there is one more chapter still to come. The final one, where we ask not just what black holes are and how they formed and what they do, but what they mean for the fate of the universe, for the future of science, for the extraordinary fact that we are here at all, in a cosmos this strange and this vast, asking these questions. But that is for another night. For now, let everything settle. Let the early universe and its turbulent feeding frenzies grow quiet. Let the little red dots fade gently, like stars at dawn. Let the dark matter and its mysteries drift into the comfortable darkness at the edge of sleep. You are here, still, breathing, a brief, curious, extraordinary creature in a universe full of black holes and dark matter and questions that outlast any single generation. Rest now. The cosmos will still be there in the morning, and it will still be full. This is the last chapter. Take a moment to feel that. Not with any sadness, but with a kind of quiet appreciation. You have traveled an extraordinary distance on this journey. From the very first words spoken in the dark, all those hours ago, to here. To the final act. The place where we look not backward at what has been discovered, but forward at what is still to come. And inward, at what it all might mean. Take a slow breath. Let it fill you, and let it go. You have learned, across this long and gentle journey, that black holes are born from dying stars and colliding neutron stars and the chaotic pressures of the infant universe. That they spin and drag space with them and slow time near their edges. That they come in sizes ranging from barely wider than a city to larger than our entire solar system. That they feed in violent, episodic frenzies and tear stars apart and fire jets across millions of light years and leave ghostly plasma bubbles above and below our galaxy. That we found them not by seeing them but by reading their shadows and their ripples and the disturbed orbits of the stars around them. That our best theories disagree about what lies at their centers. That the early universe grew its black holes through chaos and required their seeds to be enormous. And now, in this final chapter, we ask the last questions. The ones about the future. About life and fate, and what it means that we live in a universe shaped so deeply by its darkest objects. Let your body settle completely. Let sleep be close. And let the universe offer you one last set of wonders before you rest. Here is a thought that sits at the very edge of what science permits itself to imagine. A black hole's gravity is, in its fundamental character, no different from the gravity of a star of equal mass. Both curve space-time. Both hold objects in orbit. Both follow exactly the same mathematical rules. If our sun was somehow replaced by a black hole of identical mass, which is not possible, but bear with the thought, the Earth would continue in its orbit unchanged. The darkness at the center would not pull us in any more powerfully than the sun's gravity does now. We would simply lose our light. This means that planets can, in principle, orbit black holes stably, in the same way that planets orbit stars, following their elliptical paths, held in place by the balance of gravity and orbital momentum. A planet orbiting a black hole would experience the same gravitational environment as a planet orbiting a star of equivalent mass. And some scientists have gone further. For a supermassive black hole actively feeding, surrounded by an accretion disk blazing with energy and heat and radiation, that disk could, in principle, serve as an energy source. Not sunlight, exactly, but radiation, warmth. Energy arriving at a planet in orbit from the glow of the material falling into the black hole nearby. Could life exist in such a place? The conditions would be extreme. The radiation environment harsh. The geometry of orbiting a black hole rather than a star presents challenges that don't arise in an ordinary stellar system. But the laws of physics do not explicitly forbid it. We have found life on Earth in environments that were once considered completely incompatible with biology, in boiling acidic springs, in the crushing pressure of ocean trenches, in the frozen rock of Antarctica. Life, it turns out, is more flexible than we tend to assume. A planet, orbiting a black hole, bathed in the glow of an accretion disk. Something living there, looking up at a sky that glows from one direction with the light of infalling matter, with darkness at its center. The universe permits it. Whether it has arranged it anywhere, that remains unknown. We have visited the Fermi bubbles before, twice now, because they reward more than one encounter. But in this final chapter, in the context of what the future holds for our own galaxy, they take on a slightly different color. Sagittarius A*, the black hole at the center of our galaxy, is quiet now. Relatively quiet. It consumes small amounts of material, the occasional cloud of gas drifting too close, the outer layers of stars passing within reach, and it flickers in X-rays accordingly. But it does not blaze. It does not fire jets that reshape the structure of the Milky Way. It is, by the standards of active galactic nuclei, almost sedate. But the Fermi bubbles tell us it was not always so. Millions of years ago, in the deep past, before our species or our genus or most of the animals we would recognize had evolved, Sagittarius A* erupted. Something large fell in. Something that triggered an outburst of energy vastly beyond its current quiet activity. And the energy of that eruption expanded outward, above and below the disk of the galaxy, forming the two enormous plasma structures we discovered only in 2010. Structures that are still there, still glowing in gamma rays, still expanding slowly into the space around our galaxy. It happened before, and it will, in all probability, happen again. In about 4 billion years, the Milky Way and the Andromeda Galaxy will collide. The two largest members of our local group of galaxies, currently approaching each other at about 110 kilometers per second, will begin their long gravitational dance and eventually merge into a single, larger elliptical galaxy. When that happens, vast quantities of gas and stellar material will be disturbed and driven toward the center of the merged system. And the two supermassive black holes at the respective centers of the Milky Way and Andromeda, Sagittarius A*, and Andromeda's own central black hole, which is significantly more massive, will eventually find each other, orbit each other, and merge. The gravitational wave signal from that merger will be extraordinary. The subsequent activity of the combined black hole, fed by the disrupted gas of two merged galaxies, may briefly turn our descendant galaxy into something resembling a quasar. The quiet monster at the heart of our galaxy has a dramatic future ahead of it. It is simply waiting, at the moment. Patient and dark and ancient. And the Fermi bubbles are its reminder to the rest of us that patience is not the same as permanence. Let your breathing deepen. Let the thought of 4 billion years and galactic mergers drift gently through your mind without any urgency attached to it. It is a long time away. The universe has time. We have touched several times on the hidden black holes, those concealed behind curtains of gas and dust, invisible to previous surveys, only now beginning to be found through improved techniques and greater instrumental sensitivity. In March 2025, hundreds of them were uncovered in a relatively small survey. Hundreds that had been there all along, simply hidden. And the implication, extrapolated carefully across the full observable universe, is staggering. The total number of black holes in the cosmos, including those obscured by dust and gas, those too small and quiet to have been detected, those in regions of sky not yet carefully surveyed, may be not millions, not billions, but trillions. Trillions of black holes. Each one a region of space-time curved so severely that nothing can leave. Each one the product of a star's death, or a direct collapse in the early universe, or a merger of smaller objects accumulated over billions of years. Each one moving through the dark, influencing the matter around it, waiting to be found by a civilization with the right instruments pointed in the right direction. The observable universe contains roughly 2 trillion galaxies. If each galaxy comparable in size to the Milky Way hosts tens of millions of stellar mass black holes in addition to its central supermassive one, and we have no strong reason to think ours is unusual in this regard, then the number of black holes in the observable universe is a number that defies easy expression. We have found, between us, a vanishingly small fraction of them. The rest are out there, patient, dark, and waiting for us to look. Among the most exciting developments in black hole astronomy is the instrument being designed to look harder and more clearly than anything that has come before. The next generation Event Horizon Telescope, the ENGEHT, is already in development. We have mentioned it before in our chapter on detection. But in this final chapter, the context is the future. What comes next? What humanity is building right now, with the specific intention of seeing what has never been seen. The current Event Horizon Telescope gave us two still images, M87's black hole in 2019 and Sagittarius A** in 2022. Static pictures. Extraordinary achievements, requiring years of data processing and the synchronization of telescopes across the entire planet. But still images, nonetheless. The ENGEHT aims to go dramatically further. By adding space-based antennas to the array, telescopes in orbit, extending the baseline far beyond the diameter of Earth, the resolution achievable increases substantially. Enough, potentially, to resolve individual features within the photon sphere. Enough to see the accretion disk not as a blurred ring but as a structured, detailed environment. And the goal is not just sharper images. It is motion. Real-time video of the region around a black hole, updating fast enough to capture the dynamics of infalling matter. Material spiraling inward. The jet formation zone. The flickering and fluctuating structure of the photon sphere as material passes through it. To watch, in something approaching real time, the last moments of matter before it crosses the event horizon. The closest humanity will ever come to seeing inside a black hole. We will never see what lies beyond the event horizon. The physics of the situation ensures that with absolute finality. But we will see, with this instrument, everything right up to the edge. Everything that can be seen, rendered in as much detail as the laws of physics and the size of our planet and the technology of our civilization will allow. That instrument is being designed now, by people alive today. It will see what no human being has ever seen, and what it shows us will rewrite, in ways we cannot fully anticipate, our understanding of the universe's darkest places. Deserves acknowledgement as we near the end of this journey. A moment that speaks to where we are, right now, in the history of black hole science. The Simons Foundation, a major supporter of fundamental scientific research, dedicated its entire 2026 physics lecture series to black holes. Not a single talk. Not a short symposium. An entire year's worth of the most prestigious physics lectures the Foundation organizes, devoted to a single topic. The subjects covered include high-resolution black hole imaging, gravitational wave astronomy, the information paradox, analog black holes in laboratory systems, and the role of black holes in early galaxy formation. Almost every major theme we have visited in this journey. The decision to dedicate an entire lecture series to black holes reflects something real about the state of the field. We are living through an extraordinary moment. A moment when gravitational wave detectors are regularly announcing new mergers. When the James Webb Space Telescope is appending our models of early black hole growth. When new imaging techniques are sharpening our view of black hole shadows year by year. When laboratory analog black holes are testing Hawking's predictions in controlled settings. When the information paradox is seeing its first genuine mathematical progress after decades of stalemate. Black holes have moved from the theoretical periphery to the center of modern physics. Not because physicists chose to emphasize them, but because the universe, when examined carefully with good instruments, keeps pointing back to them. They are not a curiosity. They are load-bearing structures in the architecture of the cosmos. And the science is moving fast. Faster than at any previous point in the history of the field. The lectures being given in 2026 will contain results and ideas that did not exist in 2020. The lectures given in 2030 will contain results that do not exist yet. The field is in motion, and the direction of that motion is toward understanding. Let the sense of that motion settle into you. Not urgency, motion without urgency. The slow, steady forward movement of human understanding, generation by generation, instrument by instrument, equation by equation. Let's rest now with something that has been woven through this entire journey, and that deserves a final, quiet moment of attention in this last chapter. The information paradox. The question of what happens to the information content of everything that falls into a black hole. Whether the universe keeps its records, or whether black holes are places where the cosmic ledger has pages torn out. We have been watching this question approach a resolution slowly, over decades. Hawking's original calculation, suggesting information was lost. The famous bet between Hawking, Thorne, and Preskill. Hawking's concession in 2004. The 2020 breakthrough using quantum gravity calculations, showing that information is encoded in Hawking radiation as the black hole evaporates. The fuzzball proposal from string theory, suggesting information is never truly lost inside but woven into the structure of the black hole from the start. None of these is a complete resolution. The paradox is not fully solved. The precise mechanism by which information escapes, how exactly the details of everything that ever fell and end up encoded in the outgoing radiation, is still not understood at the level of a complete, mathematically rigorous theory. But the direction is clear. Across multiple approaches, from multiple directions, using multiple theoretical frameworks, the evidence points the same way. Information is preserved. The universe keeps its records. What falls into a black hole is not gone, it is hidden. Scrambled to an extraordinary degree. Encoded in correlations between particles of Hawking radiation spread across the universe. But there. The laws of quantum mechanics, it seems, hold even at the event horizon of the darkest object in the cosmos. The universe does not tear pages from its ledger. It writes in a language that is very, very difficult to read, but it writes. Very end of everything, not the end of this journey, but the end of the universe itself, there is Hawking radiation. We have met it several times. The slow, quiet evaporation of black holes through quantum effects at the event horizon. Particle pairs flickering into existence at the boundary, one falling in and one escaping, carrying away a tiny fraction of the black hole's mass. Repeated over unimaginable timescales, until the black hole is gone. The numbers involved are difficult to hold. A stellar mass black hole, evaporating through Hawking radiation alone, would take approximately 10 to the power of 6 to 7 years to completely evaporate. That is a number so large that the current age of the universe, 13.8 billion years, a number that already defies ordinary intuition, is, by comparison, essentially zero. Not small. Not brief. Zero. A rounding error beneath the resolution of the timescale involved. A supermassive black hole, something like Sagittarius A*, with 4 million solar masses, would take incomparably longer. The timescale stretches to numbers that require scientific notation to express and imagination to approach even approximately. But eventually, after all the stars have burned out, after all the remaining matter has either fallen into black holes or decayed into its constituent particles, after the universe has grown cold and dark and spread itself so thin that meaningful events become vanishingly rare, the black holes will go. One by one. The smallest first, then the larger ones, then the supermassive giants. Each one dimming slowly. Each one growing hotter as it shrinks, paradoxically, because smaller black holes radiate at higher temperatures. And finally, a last brief burst of radiation, a final release of energy, and then nothing. The black hole era will end. The universe will be left with only the faintest whisper of radiation and an expanding, cooling void. And in that void, the information of everything that ever existed will be encoded, in principle, retrievable, in the correlations of particles spread across unimaginable distances. The universe ends quietly, and it keeps its records to the last. Take a breath, slow and deep, and let it go. You have reached the end. Not the end of the universe, that is a long way off, even in cosmic terms. But the end of this journey. 10 chapters. Hundreds of millions of light years. Billions of years of cosmic history. The birth and feeding and collision and slow death of the most extraordinary objects the universe has ever produced. We began with a name. A phrase coined in 1967 by a man at a lectern, trying to describe something that defied ordinary language. Black hole. 2 words that somehow captured the weight of what these objects are, what they mean, what they do to space and time and matter and light. And we end here, in the quiet, with a picture of the universe that is different from the one most of us were given. A universe threaded through with dark objects that we cannot see but can find. A universe whose galaxies are shaped by the monsters at their centers. A universe that keeps its information even in the face of its darkest processes. A universe that will, in the incomprehensible depths of future time, grow quiet as its last black holes evaporate and their stored information spreads across the void. A universe that is strange beyond easy imagining. And yet a universe that plays by rules, rules that mathematics can describe, and that human minds have reached out across the light years and the billions of years to find. We are small creatures, briefly alive, on a pale dot orbiting a medium star in an outer arm of a galaxy that contains tens of millions of black holes and is itself orbiting a central black hole 4 million times the mass of the Sun. And we know this. We found it out. With our instruments and our equations and our extraordinary, restless curiosity, we looked up at the dark and we found what was hiding in it. That is not a small thing. That may be the most remarkable thing about the universe, not that it contains black holes, as extraordinary as they are, but that it contains something capable of finding them. Let the black holes be out there in the dark, as they always are, spinning, feeding, evaporating over trillions of years, warping space around them, keeping their ancient records in the language of Hawking radiation. Let Sagittarius A** sit quietly at the heart of your galaxy, for million solar masses of patience, 26,000 light-years away. Let the little red dots glow at the edge of the observable universe, ancient and ravenous and full of questions we are only beginning to answer. Let the gravitational waves from a billion mergers ripple through you right now, gentle as a whisper, undetected, carrying their information outward in every direction at the speed of light. You are part of this universe, made of the same matter that once lived inside stars that died and whose remnants became the world you inhabit. You are, in the most literal sense, a product of stellar death. The same process that produces black holes also scattered the heavy atoms of which you are made. The universe made black holes. And then, in the same breath, it made you. Rest